Som. Alô, não.
Tá. Connected? I think probably they do it. We should do. You are doing? Você vai conectado? Opa. Tá bom? Você me fala quando eu posso começar? Okay. So we can start our meeting. It is my pleasure to organize the workshop of our group on algebraic structure in field theory. And it is my pleasure to have invited speaker from abroad and from Brazil, Professor Naruhiko Eizawa, our collaborator from Osaka Metropolitan University in Japan, Professor Mauricio Valenzuela from Chile, Universidade de San Sebastián and o Centro de Valdivia, a professora Jana Kuznetsova da UFABC em Santo André, São Paulo, e os estudantes, 4 estudantes de doutorado aqui do CBPF. Nós temos programa, we have an intense program. So the first speaker is Professor Naruhiko Eizawa. You see the title of the talk, please.
Okay, thank you very much. First of all, I'd like to thank Professor Toppan for organizing this exciting meeting. This is very nice because this is a combination of senior talks and young talks, which is quite a rare opportunity. At least I have never participated in this type of conference before. Okay, let me start my talk. Today I'm going to talk about something strange things, which is following. The purpose of this talk is to okay. The purpose of this talk is to develop some superfield formulation of Z2 supersymmetry. So in this talk, we work out with a simple example, which is the minimal Z2 superspace. But the result which we can obtain is quite fluid in the sense we produce many interesting models. And this simple example can be extendable to more complicated cases. So this is the plan of my talk. Probably many of you are already familiar with the Z2 business, but let me start with explaining what is Z2 supersymmetry. And then I'll give you the motivation of my personal motivation of studying this. I'll talk about 3 motivations. Then I will tell you the superfield formulation, which we developed recently. So we introduce what the superspace is and how to define the superfield and what is the supersymmetry, Z2 version of supersymmetry transformation and how to construct action. Now let us start introduction. So suppose that this is a classical action. Any action is okay. But further, we suppose that this action is invariant under a certain continuous transformation. And as you know, in many cases, continuous transformations are generated by real algebra or super algebras. But there is no need to restrict ourselves to these algebraic structures. Indeed, there is another object which also generates a continuous transformation. One of them, there are several of them, but one of them is the so-called higher graded real algebras, which was introduced by Lee in 1960. After some years, the same object has been discovered by the physicists Rittenberg and Weier's. This is a quite natural generalization of the superalgebra. So this has, although this has a very long history, but not extensively studied until recently. Because of this, there is no fixed name. Some people call these color algebras or generalized real algebras, or in early literature, this is called epsilon real algebra. So for the moment, I'd like to call it higher grade real algebras and super algebra and so on. So this is a class of this is a class of an algebra which is close similar to the algebras. But today, I'd like to pick one of them, one of the particular example of this algebra, which is a Z2 version of supersymmetry algebra. This is nothing but the Z2 graded version of one-dimensional super-Poincare algebra. This algebra was introduced by Bruce in 2019. That, maybe you're not familiar with this. Z2 is an abbreviation of Z2 times Z2, and Z2 is an order 2 abelian group with element 0 and 1. Now, this is an algebra. This is a Z2 supersymmetry algebra introduced by Bruce. This is a four-dimensional algebra whose relations are defined, given by these relations. So this consists of the commutators and uncommutators, but this is not a super algebra in the following sense. This is a Z2 graded. It means the underlying underlying vector space is Z2 graded. Namely, each element has a Z2 degree, which is an element of this Z2 abelian group. For instance, H is degree 0, 0, Z is degree 1, 1, and so on. And commutator or uncommutator is determined by the degree. So so let A and B be an element of Z2. Because this is a two-dimensional vector, you can regard this as a two-dimensional vector. You can calculate the inner product of these two. For instance, if you take H and if you also take Z, then there are two-dimensional vectors. You can calculate the inner product. This gives you 0. If the inner product is even, you take the commutator. So here, H and Z is closed in the formula. On the other hand, if you take Z, if you take Z and Q1, 0, the inner product is 1. Inner product is all. In this case, we use anticommutator. So here, Z and Q1, 0 close in the anticommutator in this way. Okay, so this is the basic idea of the Z2 supersymmetry algebra. Now, let us compare this Z2 version of supersymmetry to ordinary supersymmetry algebra of n equal 2. This is an n equal to supersymmetry algebra. This is Z2 graded three-dimensional algebras. The relation is given here. So just compare these two. The black part is more or less same. But you can see the difference in the red part. In the ordinary supersymmetry, two supercharges are antitomy. While in this Z2 version, two supercharges rolled in the commutator and gives you another element. If D consists of two supercharges, so D must be boson in a sense. So looking at these two algebras, what we can learn immediately is the following. For supersymmetric case, ordinary supersymmetric case, there are only two types of objects, bosonic one and fermionic one. On the other hand, that to the extension, you have four different types of objects. One bosonic, one more bosonic, which degrees 1, and two types of fermionic. So this is always true. Everything you encountered in this business, in the ordinary super case, there are two types of objects. In the retrofit case, there are always four different types of objects. And if you realize this supersymmetry algebra in a quantum mechanical way using the Hilbert space and the differential operators, what you can obtain is the so-called supersymmetry quantum mechanics introduced by Wittgen. And if you do the same for this version of supersymmetry algebra, what you get is the supersymmetry quantum mechanics, which was introduced by Wittgen. Now, this is an algebra. So let's move on the motivation of the study of this algebra. I give you three motivations. Number one is the experimental realization of paraparticles. And this is what's quite recent thing. The paraparticle was introduced very long time ago. Paraparticles are not fermion, not boson, but so to say, they are just in between, because the occupation number of fermion is just 1. The occupation number, possible occupation number of boson is infinity. So there are two extremes. The paraparticles are in between. Their occupation number is finite, not 1, not infinite. So these particles are in between. But unfortunately, up to now, these paraparticles are not found in nature. However, these people did some experiment, and they asserted that paraparticles are realized by a laser-driven trapped ion. This is some figure. This black circle indicates an ion, and these red lines are laser beams. These red lines crossing perpendiculars are laser beams. So using laser beams, they trap the ion. So the ion is sitting there. It is cool. It is cool. Cooled ion. Then this is an interacting system of the spin of the ion and the laser photons. Okay. So if you do fine tune of this orthogonal lasers, which means you adjust the frequency, strength, or maybe the angle and so on. I do not know the detail. But if you can do the fine tune of this laser beams, this system combined with the spin and the photon is effectively equivalent to the paraparticles. This is the result of their experiment. I took this figure from this paper. The horizontal axis is time. The vertical axis is the expectation value of the number operator of the parafermion. And this dashed line is a theoretical computation. And this dotted line is an experiment. So there is a very nice agreement. So they, with this figure, they assume so they assert that parafermion experimentally realized. So what is important here is if you can control quantum systems appropriately, you can simulate paraparticles. And there is a deep connection between the paraparticle and Z2 supersymmetry, Z2 superalgebra. In 2024, Tolstoy pointed out that mixed system of boson and parafermions gives you a Z2 superalgebra. If you think only parafermion, that it doesn't make no connection to Z2, but you mix them, then the whole system throws in a Z2 superalgebra. And as I already mentioned, if you consider the Z2 supersymmetry, it is automatically introduce a new kind of particle which is neither boson nor fermion. They are particle. So if you can do the appropriate control of quantum system, there is a possibility of experimentally realized veto-to gradient system. So this is quite exciting. The second motivation is the veto-to version of Sine-Gordon equations, which was introduced by Toulouse 2 years ago. So let me remind you what Sine-Gordon equation is. A Sine-Gordon equation is a nonlinear partial differential equation having Soicon solution. And this is an equation. Here you have a sine interaction given by a sine function. And the Soicon solution is given here. This is an example, one Soicon solution. This is a snapshot of the solution. It means the horizontal lines, the vertical lines is high. So at the fixed time, the solution looks like this shape. And if time goes, this shape does not destroy. The solution keeps this shape. And this shape is moving toward left or right if time goes. So this is a Soicon solution. This is just the simplest one Soicon solution. And this system is known as integrable in the following sense. You can start from one Soicon solution. Immediately, you can get two Soicon solutions. Then, using this two Soicon solution, you can get three Soicon solutions, and so on and so on. This is done by the so-called background transformation. This kind of transformation. So you can, starting from the simplest solution, you can get many solutions. In addition to these, you can show that there exists infinite many number of constant of motions. You know, this equation is defined on 1+1 dimensional space-time. So the dynamical degrees of freedom of this system is infinite many degrees of dynamical freedom. And it is known that if you can find the constant of motion, same numbers of constant of motion as the degree of freedom, then you can solve the equation. So in this case, that really happens. That really happens. This is an infinite degree of, this has an infinite degree of freedom, and there is an infinite many constant of motion. So in this sense, this system is solvable. Okay, this is a Sine-Gordon equation. And what Bruce did is he introduced Z22 version of Sine-Gordon equation. He started from Z22 supersymmetry algebra in two-dimensional space. And he introduced the covariant, so to say, covariant derivative. This is a supersymmetric derivative. And using this derivative, he wrote down something similar, equation something similar to Sine-Gordon. Okay. And so in this sense, this equation is related to the supersymmetric equation. And he showed that there exists the background transformation to this system. Same idea. And he also showed there exists infinite many conserved quantities. So using these observations, he claimed that this system is integrable too. So this is just a simple one example. But I think this suggests there exists a wider class, new class of integrable systems, which is characterized by Z2 symmetry. I think this is really an exciting area of research. So this is my second motivation. Third motivation is from a geometry, supergeometry. I'm not sure this is familiar or not. You know, let us think differential geometry of ordinary manifold, not supermanifold. The differential geometry of the supermanifold can be done using supersymmetric quantum mechanics. Why? Because this is ordinary manifold and this is supersymmetry. So at first glance, there is no fermionic object in this, but there are two examples of the fermionic object in the differential geometry. Number one is the differential form. Differential forms are by definition antiformic. So this is something like a fermion. Another one is exterior derivative. Exterior derivative acting on the function or differential forms and gives you a higher degree of higher degree differential form. But if you do that twice, you apply the exterior derivative twice, then it always gives you 0. So this is also something like a Fermi. And in fact, there is a thing which is called the Doran complex in differential geometry for real manifold. Doran complex is an Hilbert space of differential forms with this exterior derivative and this Hermitian conjugate. And this delta defined by the anticommutator of the Hermitian conjugate corresponding to a Laplacian in curved space. And of course, there is a differential form. And this Doran complex is a one-to-one correspondence of the supersymmetric quantum mechanics. Because if you take the n equal to supersymmetry and use a complex representation, supercharges complex map, Q and Q lambda, then square of Q, square of supercharge is 0. Is something like this. So is Q lambda. And Hamiltonian is given by the anticommutator of Q and Q lambda. The Hamiltonian corresponding to the lab in differential geometry. And what corresponding to the K form is wave function of this Hamiltonian having K fermions. But what is the contact of this system, this quantum mechanical system and manifold? It's coming from the classical level. In fact, this quantum system is obtained by quantizing this Lagrangian. Here, G, this G is a metric of the manifold under consideration. And phi is the superfield. In this way, superfield comes in the game of that geometry, right? Now, this is an ordinary manifold, but if you consider super manifold, then what happens? What happens is the following. I have to explain the definition of supermanifold. A supermanifold is a manifold whose local coordinate is given by the real number and the Grassmann number. In this case, the differential form of supermanifold is deductive commutative algebra, because the differential form of the real number aren't commutative. But the differential form of Grassmann number is commutative. Now we encounter that two. So I have a speculation. This is just a speculation. No reason. If you consider Doran complex or supermanifold, that can be described by the Z22 version of supersymmetry. If it is so, we have to formulate this supersymmetry starting from the classical action, which is described by the Z22 version of the superfield, just like before. So it's just a speculation. I hope this works well. But this, at least this is the motivation of studying the Z22 supersymmetry. Okay. Now let us turn to the superfield formulation of the Z22 supersymmetry. So let me say one more time the purpose. The purpose is to construct classical action which is invariant under Z22 supersymmetric transformation by a superfield. To this end, all what we need to find is to find dynamic variable. And Z22 supersymmetric transformation of these dynamic variables. How to write down the invariant. And what we have observed in the recent paper is the following. The generalization of the ordinary superfield method to Z22 setting is possible. And this problem solves all these problems easily. So let me explain this step by step. So we can start with a very group theoretical way. We have another Z22 supersymmetry algebra. So let us consider group element by exponentiating the algebra. So we have to introduce some parameter. Because the exponential argument of exponential cannot be any degree, so the introduced parameter must have the same degree as the generator of the algebra. Okay. Then this is the parameter. So they are commutative, but they have a degree. So that they must be commutative, which means these parameters must satisfy these relations. If T commute with everything, so this is a C number, and Z is uncommute with theta, and theta commute each other, and theta is nilpotent, so these are fermions. But Z is not fermion. Square of Z is not zero. Now we define the minimal Z to the superspace. The minimal Z to the superspace is the non-commutative space whose coordinate is given by this parameter. Actually, this is the simplest example of Z to the supermanifold, which is discussed by these people. And physically, you can interpret this C number T as a time coordinate. So we have one time coordinate and three other non-commutative coordinates to consider such space. Then we consider the transformation of this non-commutative coordinate, which is also given by the theoretical way. The coordinate change can be caused by the left action of the group. So this G is this G. We introduce another G whose parameter is now written as epsilon. Then take a product, you can calculate, then the original parameter of G, T, theta, etc. is changed by this multiplication. More explicitly, if you consider infinitesimal transformation, coordinate change is given, for instance, this formula. The details are not important, just you can do this kind of computation. Now we also introduce Lorentz transformation. This is not a real transformation because this mix the time coordinate and the non-commutative one. So this is an example, definition of the Lorentz transformation. And what we can see is generators of this transformation, I mean the supersymmetry transformation and Lorentz transformation goes in a 5-dimensional vector supergroup. This is the definition of generator. You can, if you know, you can skip this. Anyway, sorry. I use the same notation for generator and algebra. Probably this does not, yes. Okay. The algebra is 5-dimensional. There are 5 elements. Space time is 4. Actually, non-commutative space is 14. So this is the generator of the generator of the translation goes in a Z2 superalgebra as we expected. And this is a relation between the Lorentz generator and the algebra. This looks nice. Hamilton H goes to T, and supercharges are rotated in a nice way. Now we come to definition of the superfield. The superfield is a function. This is the definition. Superfield is a function of the Z2 superspace. It's given here. Function of the Z2 superspace of homogeneous degree 0, 0. This is not necessary to be 0, 0, but for the sake of simplicity, here I assume this is degree 0, 0. And in addition, this function is invariant under Z2 supersymmetry transformation and Lorentz transformation given in the previous slide. This transformation. We assume that the function is invariant under this transformation. Now, let's look at these two conditions in some more detail. The condition number 1 asks, the condition number 1 is this. This is the function of non-commutative variables. But as you know, sheeters are nilpotent. So if you expand this function in Z sheeters, then sheeter terminates up to this term. But Z is not nilpotent, so the function is a power sheet in Z. So we correct the even term in Z and odd term in Z. Then you can have this kind of expression. you can have this kind of expression. The first term, y is a z square. So the first term is the even in z and do not contain any sheet. The second term is, yeah, you have another like that. Second term is the odd in z and do not contain any sheet. This term contains one sheet, this term contains one sheet. You can expand the function in this way. And we take this we take this 8 component field as a dynamical variable. Because the left-hand side is degree 0, 0, and z theta has degree. So the component must have degree 2. And their degree is indicated by the suffix. So there are 4 bosonic dynamical variables and another 4 fermionic variables. Okay. Now let us look at the invariance under the transformation. This function does not change if you do the coordinate change, but it means you change the coordinate. So the component must change in such a way to cancel the change caused by the coordinate. The coordinate change and change of the component must cancel each other. Otherwise, the whole function cannot be invariant. So in this way, you can, starting from the coordinate change, you can automatically obtain the change of the dynamical variables. Here, this is some example. This is a coordinate change by the supercharge. Then the component must transform in this way. For instance, bosonic degree, bosonic variable to fermionic one, fermionic variable to bosonic one, etc. This is an coordinate. This is the transformation caused by Lorentz transformation of the coordinate. So there is no mixture of boson and fermion, but the degrees are changed by this transformation. Yeah. Degree 0, 0 goes to degree 1, 1, and degree 1, 0 goes to degree 0, 1. So this kind of transformation. So in fact, this is the transformation. This is the supersymmetric transformation of the dynamical variables. Okay, now we have everything. We have the dynamical variable and their transformation. What we have to do next is to write down the action which is invariant under this transformation. And that is a quite easy task. This is the reason. If you consider this kind of combination, this is automatically invariant, as I will explain. There are some remarks. This alpha is a coupling constant, but this has degree. And B is a degree 0, 0 function of the superfield. Any function is okay if it is degree 0. And this D10, D01 is a supersymmetric covariant derivative. We don't know the explicit formula. It's just a covariant derivative. I will explain what this is later. The invariance of this action. Okay. Another important thing is this is the integration on the superspace. Okay. The invariance of this action can be understood in the following way. First, there are 3 obviously invariant things. The number 1 is the integral measure. If you do the supersymmetry or Lorentz transformation, this does not change because the Berezinian, this is the Jacobian transformation, is 1. This is just an easy game of computation. If you do the computation, you can see this is 1. So this is invariant. And this strange combination z over square root of y, this is also invariant for any change of z. Because change of g causes change of y. So you can see, immediately check, this is invariant. And this part, d of phi is invariant by definition. Phi is invariant. The function of phi is also invariant. So this is invariant, this is invariant, and this is invariant. What rest is this part containing d. And the covariant derivative means this d10 phi and d01 phi is supersymmetric invariant. Actually, this is the definition of covariant derivative. Usually phi is invariant, but even if phi is invariant, if you take a derivative of phi, it's not invariant. But covariant derivative is defined in such a way, this derivative is also invariant. So these guys are invariant. But unfortunately, this is the supersymmetric covariant derivative. This is not invariant under the Lorentz transformation. But fortunately, if you take a product, this is Lorentz invariant. You can check this by direct computation. So appearing here, the objects appearing here are all invariant. So this is invariant. Now, we can perform the integration. And in fact, there is some problem about the integration. So we employ the integration defined in our recent paper. The definition of integral is the following. This is a function from the superspace, and we can expand the function in this way. We can expand the function in this way. And the integration on the superspace defined in this formula, in which only the terms proportional to z theta 10, theta 01 contribute to the integration. And this integration is defined in the ordinary two-dimensional space. Here, t and y is real number, no longer the non-commutative one. And there are some remarks in order. In fact, the integration on z to the supermanifold has been investigated only for the minimal z to the superspace. Only in this case we are discussing now. No other case has not been discussed here. And this is one of the definitions of integral, and there exists other definitions of integration. But we use this because this is appropriate for our purpose. So anyway, we employ this definition and calculate the integration I showed you in the previous slide. This is the integration. By definition, if you perform the integration, you can get something like this. Two-dimensional integration. Then you take the square root of y and call it x. And you also do some definition of the variables. Then you can get the two-dimensional field theory, which is set to the supersymmetry. This is a system we go. Action now can be written in this way, and Lagrange is written by this one. So this is the kinetic term. This is the kinetic term of the exotic boson. And from this formula, Lagrange, you see A00, A11 does not propagate. These are auxiliary field. And here you have two component Fermi, which is defined. And you have B00 and B11. They are the function of the bosonic field. And this can be any function provided that this condition is true. So this contains a quite general interaction term between bosons and the fermions. So using this expression, you can obtain many supersymmetry extension of many known models. So we just give you two simple examples. The first example is the version of the Sinch-Gordon equation. For this, we take the potential B is cos A, cos theta. Here, I write down the equations of motion, not Lagrangian. Equations of motion is obtained by the Euler-Lagrange equation as usual, because we have Lagrange. So this is a system of equations, differential equations. There is a coupling between bosons and between the bosons and the fermions. And if you delete all the fermionic variables and exotic bosons, what remains is this. This is a so-called Sinch-Gordon equation. So this system of equation can be regarded as a to the extension of the Sinch-Gordon equation. And by construction, this has a that to supersymmetry and wet environment. The second example of this real model. For this, we take V with just exponential pi to super T. Here, again, we have the equation of motion. And if you eliminate all the Fermi-Newton variables and the exotic boson, what you get is this one. This one. This is the so-called Liouville equation. So this system of equation is the extension of the Liouville model. And since Gordon equation and the Liouville equations are known as integrable, the equation we introduced now, integrability of the equation we introduced now are not solved yet. This is an open question at this moment. But checking the integrability of this equation will be quite exciting topic. One can do. Okay, this is all what I want to say today. So let me summarize my talk and give you some concluding remarks. The summary is the following. We developed the superfield method for the minimal Z2 superspace. And using this, we can introduce the Z2 extension of the Shinch-Gordon equation, Liouville equation. And if you take an appropriate choice of the potential B, you can have more and more different systems. But this is just the beginning. There are many things to be done. For instance, we restrict ourselves to the minimal Z2 superspace, but no need to restrict them. If you extend the superspace, what you obtain, you have the system with more supercharging. So to say, n equals 2, n equals 3, n equals 4, and so on. But to this end, we need the integration. We need to develop the integration theory of the supermanifold. This is a very mathematical challenging problem, and I think it's quite interesting and important. And we saw some possible integrable systems. So search for new integrable systems, which is characterized by depth-to algebra, is quite exciting for me. And we just show you the classical system. Of course, you should quantize. Then what you have is the quantum field theory, it's depth-to supersymmetry. And today I talked only on the depth-to supersymmetry algebra, but of course you can consider other depth-to algebras. So there are many things to do. So I'm very excited about these topics. So that's it. Thank you very much.
Thanks, speaker. And please, any question, especially from students, and not only students. Okay. That's okay.
Why did you put z divided by square root of y, or y is integral?
This factor is necessary to have an appropriate kinetic term. If you drop this term, you cannot get this kind of terms. So you want this term. Okay. So we want this term. And by the definition of integration, by the definition of integration, only the term proportional to z, g, theta 1, 0, theta 0, 1 survived. So we want the surviving term must have this kind of structure. And this term is, to this end, we need this factor. Because you have Z here. That picks up an appropriate combination from terms in the bracket.
Rodrigo.
Hi. How do you interpret the gradient changing in the Lorentz transformation? I mean, in a physical way.
You know, this definition of integral is quite strange because at the end of the day, the z variable is changed to y variable, and eventually, it's here. Eventually, by this transformation, original g goes to x. You know, that is degree 1, but this x has degree 0, 0. So by integration, the degree 1 bosonic variables is converted to degree 0, 0 variables. In this way, we obtain the two-dimensional theory defined on t and x space-time coordinate of t and x. So if you have the theory on two-dimensional space, there should be some Lorentz transformation. At least I thought so. Actually, this has a Lorentz transformation, which I did not put in the slide, but you have the transformation of the t and x, and it also transforms the variables appearing here. But our construction is starting from the superspace, superfield. So I thought even at that level, at the level of the superspace and the superfield, there should be some transformation which eventually becomes the ordinary Lorentz transformation. So in the beginning, my Lorentz transformation looks very strange. That changes the degree. But at the end of the day, that becomes normal Lorentz transformation. So I think there is no contradiction of interpretation. Beginning is strange, but what we obtain eventually is quite a normal system. Is it okay?
Thank you. Nice talk. In this Lagrangian, actually, how are the degrees of the field preserved? And when you have two fields, the quadratic product of these fields, when you exchange the order of the fields, what are the phases that come after the exchange? For example, for fermions, if you have a term like Dirac term, you exchange the order of two psi fields and you get phase -1 because they are grasping. And also this property is useful if you want to prove hermiticity of the Lagrangian. So how that works here?
That's an important point. Thank you for the question. So the phase or commutation relation of these variables are governed by the Z22 structure of the theory. So we did some integration, but even after the integration was done, the variable still has the Z22 degree indicated by the suffix. So if you exchange 2 psi 10 and lambda 10, you have minus sign. This is definition of Z22. And if you exchange psi 10 lambda 01, you don't have any sign. That's one. This is also coming from the definition of algebra. And we suppose that all the fields appearing here is real. I didn't tell, but we construct the theory in such a way. So this is the real Lagrangian.
Just one question. Can you show the once more, please, the equations of derived Sigaud model? This is one of the version of the theory. Yeah. I have a comment for students because I think there is a very interesting point that he mentioned concerning the relation of geometry, the ramp homology, and n equal to supersymmetry. And the point is that for n equal to for supersymmetry, you have systems which are dynamical, but with the same kind of structure, when you realize with nilpotent operator, you can construct a topological theory. So the question is the following: did you think to make not only dynamical system but topological theories with the Z2 based on cohomology?
Okay, that's a very interesting point. Now that I'd like to consider about that, but for the moment, I have no idea about that, and I have never tried in that direction.
Any further question? No? Well, if not, we thank the speaker again for very nice presentation. Thanks, Naru, for everything. And okay, we are a little bit late with the schedule because of the problem at the beginning, but we pass immediately to the next speaker, who is Rodrigo. Rodrigo Rana is a PhD student here at CBPF, and he's the first PhD student presenting today in the workshop. Please, Rodrigo.
Thank you. Hi, everyone. First of all, I'd like to thank Professor Toppan for organizing this event. So today I will talk about Zeta2 to n graded brackets presentation as Boolean logic gates and parastatistics datability. So this presentation is based on a collaboration work with Matheus Balbino, Isaac de Freitas, and Francesco Toppan. This is my presentation outline. Let's begin. So here we have the classical papers, right? We all started by reading this. And here's some recent papers, and you can see that we have many areas to investigate. But our contest is to think about the detectability of paraparticles. So we have these two papers by Professor Toppan. So we start considering an associative ring of the two to the n graded operators with the addition and multiplication operations. So the operators A, B, and so on are associated with the n gradients. So if we have n equals 1, we have only 2 gradients n equals 2, we have 2 to the power 2 grading, so 0, 0, 0, 1, 1, 0, 1, 1, and so on for any n. This satisfies the multiplication, like in expression 2. And we associate the identity operator with the zero grading. So we define a graded Lie bracket in 4, where the bilinear map alpha beta takes values 0 and 1 modulus 2. And this satisfies the graded Jacobi identities presented in 5. So just a summary, the brackets define a graded Lie superalgebra, which is compatible with the Z2 to the power n grading of the ring of operators. Right. So we have these two important definitions for physics, right? If you have a diagonal product, right? The operator with himself, and if this is a commutator, we call this Lie algebra, Z2 to power n graded Lie algebra. And if you have at least one diagonal product different for one, we have a Z2 to power n graded Lie superalgebra. So you can think about the inequivalence mappings that leads to different structures, algebraic structures. So for Lie algebras, we have the ordinary Lie algebra as a vanishing scalar product, right, in 6. And in general, you have the expression 7 for the rest of the possible mappings for a Lie algebra. For Lie superalgebras, we have the expression 8. And the total number of inequivalent Z2 to power n graded compatible Lie superalgebras is given by Bn, where the middle term n over 2 is the floor function. Some examples like B1 equals 2, B2 equals 4, and so on. Okay. Now I will do it on the board. So we start with presenting the logical gates. We have the NOT gate. And it means that you have an entry 0 and it's changed to 1, an entry 1 and changed to 0. Okay. We have the AND gate. And we have this combination 0, 0, 0, 1, 1, 0, 1, 1. And only in the last combination, we have 1. The OR gate. And we only have 0 in the first combination. And finally, the XOR gate. In XOR gate, you have only one if the entries are different. So let's take an example. I will considering the kernel maps. So we construct like this. We have the binary map with the gradient vectors with two components, and you construct the kernel map like this: alpha 1, alpha 2, beta 1, beta 2. All the combinations. You can notice that row to row and column to column, we're varying just 1 bit. And this is important to this map. So we have this. Okay. This is the structure of brackets, which the 0 represents the commutator and 1 represents the anti-commutator. This is the zeta2 graded algebra, right? We have only commutators in the diagonal. So you have this. We started by grouping the ones in powers of 2. So here in vertically and horizontally. So here we group this and this, and here. So now we look at each group and analyze which bit is varying and taken them out. So let's take this group here. You can see that in the column, we don't vary anything, but in the row, we're varying the alpha 2, sorry. So we take out the alpha 2 of the expression, and I forgot to mention that each group we have the AND gate, and between the groups we have the OR gate. So this group will have alpha 1, beta 1 with a bar, and beta 2. So we have alpha 1, and this is the AND symbol. Beta 1 bar and beta 2. The bar is for the 0 here. So in the 0, when you have the zero, you have to bar the variable, which means that you are using the not gate. Bar means the not gate. So you can construct this for each of the group. And so on. So after a few manipulations, you can, and using the Morgan's theorem, you can finally get the final expression like this. This is the XOR gate symbol. So the secret is given by this. So this is the circuit, the Boolean logic circuit, representing the zeta2 graded Lie algebra. And you can do that for any map. So we don't know yet the consequences about this construction, but it seems to me that we can at least engineering the control the quantum simulation about this type of system. So that's it about the Boolean logical gates. First. Okay. No, the numbers represent, one represents anti-commutators and zero commutators. We have the brackets definition. Thank you. So we have this structure with associated with the bracket structure. So in the one you have anti-commutator, in zero we have commutators. This is known in the Z2 case. I only use this because in bigger structures it's getting worse. Yes. This mapping too. So in superdivisions, you have the multiplication structure, and you can extract the the brackets structure using this, for example. Sorry? Yes, yes. Okay. In supersymmetry, you mean, is that true? We have only the, yes. We have only this, right? 0, 0, 0, 1. Supersymmetry. So this represents only alpha times beta, and this is the AND gate. Yes. This reproduce this in kernel maps. Okay. So we have these operators Z2 to power n graded with these gradients, and we are using the braided product, right? The definition is in the 10. So we need this. We need this to define the coproduct delta, and we use to construct multiparticle states. So this is the coproduct map, right? And some properties. Now you can construct the physical system, right, of Bn in equivalent multiparticles quantization. So we define this matrix in 15. So for n equals 1 bit case, we have this representation given in 16. For n equals 2, you have 17. And you can see that, okay, beta squared and gamma squared is 0. So the pairs of creation and annihilation operators vanishes when we take in product, and we have this algebra given in 18. So if we can construct for any n by assigning 0 to the operator, to identity operator, and 1 to anti-diagonal operator. So the n is equals to creation operators are graded like this. You can associate the 0 here with the you can associate the grading here with the number here. You simply you have to write in the right side the number in binary. So for any n, the creation operators are on equal footing and produce n equivalent to 2 to the power n graded compatible abelian these super algebras and defined by these brackets. So we have the n-bit emission Hamiltonian, even in 22. Some examples in below. We define these operators that will be important in the final with these respective gradients. So we construct now the vacuum state. This is wrong, sorry. The vacuum state is the tensor product of the one particle state. So we have this definition of the excited states of energy, level 1, given by the coproduct defined in this. In this case, the braided tensor is equal to the regular tensor product. So for energy level 2, we have a product of coproducts like this. And the nature of bracket structure is here. So this term here depends on the relations of commutation or anti-commutations given the structure. So for n equals 2, there are 4 inequivalence bracket structures given in here. And here are the number of states in each level. You can see that only in level 3, you can differentiate about the 2, 1, 2, 3 from 2, 2, 2 to 4. So we need another observable to distinguish these subgroups, right? So we can use the normalized states given by 28 and 29 expressions. So you can see here the sign can differentiate about the structures, the systems. So we use the definition of X operator before and called exchange operator. And we define this operator in 13. Sorry. And we have finally the eigenvalue that differentiates the types of structures, the types of system. So from this construction, you can see that it's theoretically possible, at least, to detect inequivalence by statistics. Some conclusions and perspectives. So the 2 to the power n graded by statistics are theoretically observables, but at least in this presentation, you don't know the physical nature of the operator Y. So we have to systematically investigate the properties for more physical systems. I finally finish with this question: is there no physical observable to differentiate different particle systems? So later in Professor Toppan's presentation. Thank you.
Thanks, Speaker Rodrigo. And please, any question?
Do you have a name for this kind of bits of set to graded bits? I don't know how we call it. Because, for example, there are bits, 2 bits, but now you have this set 2 kind of bits. Is there a name for that? Do you have a name for this kind of bits? Set to graded bits? What the other thing is that Professor Naruiko mentioned an experiment where they could test parastatistics in quantum optics. Have you thought about some possible uses in quantum optics about this?
I'm thinking about try to use this to control the variables of an experiment, for example. I don't know yet how you use this to engineering these structures, but I'm interested too. Yes, I know the paper, but I don't I don't see any relation yet.
The question, I have a comment because in fact, this paper by Bertal de Reta was one of a source of inspiration. And this idea of relating these engraded algebra, the equivalent engraded algebra with Boolean logic gates is this idea of Rodrigo, who pointed out the existence of Carnot map that was displayed in the board, and I was not even aware of the existence of Carnot map. So, and it's a possibility that to use this kind of system as a blueprint to give to some experimentalists. Very.
I think that you could make some statement about the speed to process some kind of algorithm and see with this kind of set 2 bits is faster in some way compared to virtual bits. That will be interesting if you figure out that it's faster, then it could be a motivation to study this system. And cryptography, exactly.
Now, I can imagine cryptography application. You make a lot of products for example, 5 bits, and there are number of products, yes? So you encode on these products and result will be in bits because a result of the multiplication table is 0, 1. So it can be application, I think, maybe the cryptography of its included.
I agree, but I don't know much about cryptography, so I agree. There are many possible applications. Yeah.
There was a suggestion by Luisa to apply this sort of Boolean logic gate to cellular automata. We don't know how to do it, but Luisa is an expert on cellular automata. He will presentation later, and so yeah, it's a work in progress. But I think the results are interesting.
At some point, you showed us the number of state in the multi-particle case. Can you explain briefly how to compute the number of state?
Um, here. These numbers. You simply construct these states. So for vacuum, level 1, we have only vacuum, so one state. States of level 1, sorry, yes, 1. Sorry? Yes. Sorry, the the table is wrong here. Level 1 means level 0, just vacuum. Level 2 means level 1, and level 3 level 2. Is a energy level. Right. The Hamiltonian you construct using the coproduct. Yes, in this case you have here. Yeah. Yes. 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 Typo. You can notice here too that the Pauli exclusion principle para family and families. Okay, thank you.
Well, if there are no further question, let's thank Rodrigo again for the beautiful presentation. And now we can enjoy a coffee break. We will have a little bit shorter, not 30 minutes, because please, there is some 20 minutes, let's say. 20 minutes, and then let's say 11:20 in order to, yeah, 11:20. Okay? And it's coffee is just outside it. And we can.
Mhm. The first, no, third talk of morning session given by Sir Mauricio Venezuela, from Chile, from Valdivia. So please, you can begin.
Thank you very much for being here to attend my talk, and thank you very much, Francesco, for the invitation. It's always a pleasure to come to Rio, one of my favorite cities in the world. So, London, Paris, it's competing with the big cities. Okay, so my talk is about some kind of simple fermion system that enjoy two properties. Sorry, I confused. Important properties, that is gauge symmetry and time reparameterization invariance. So I started to study this system because I realized that I didn't understand how to read the canonical analysis of gravity. Okay, so this is important for quantization of gravity, the canonical approach for quantum gravity. But there are many technical difficulties to understand gravity because the structure, the mathematical structure, too many indices, too many field components, and then you start to get confused and you lose the feeling with the intuition about the problem. So I propose some very, very simple system that enjoy these two properties that are also shared by gravity, gauge and time reparameterization invariance. So the issue is how to treat this system canonically. Okay, so you don't need this introduction to understand the system. Actually, we can just go straight to the model and study. Okay, so here there is a model for fermion particles, fermion fields in one dimension. So this is like pseudo-classical mechanics. Pseudo-classical mechanics means it's like classical mechanics with Grassmann variables as your field. Instead of position and momentum, you work with Grassmann. So here the model consists of three Grassmann variables, theta, lambda, and z. Okay, and dot means time derivative as usual, and this is the Lagrangian. So you can write an action in this form, and here the exterior derivative appears as time derivative, and omega appears like a one form. Okay. So the action is time reparameterization invariant. It means that you map the time to a function of time, reparameterizing the time. And if you perform this additional transformation, then the system is invariant. The field equations are very simple. Lambda dot is just theta, and zeta is auxiliary variable. And there is this gauge symmetry, it's a chip symmetry. Theta is chip, is like a one form or one a gauge connection. So it transforms like the derivative of this parameter epsilon, achieved by lambda, and zeta doesn't transform. So because I have this gauge symmetry, I can fix the gauge. And when I fix the gauge in this way, so theta is just proportional to lambda. I obtain the field equations for lambda that looks like the fermionic harmonic oscillator. Just that here I start with a little bit more structure and some symmetry. So the solution is very simple, just exponential times a Grassmann constant. So in the Hamiltonian formulation, we pass from from configuration space to phase space. And in that step, we realized that some constraints appear, okay? Because some in gauge system, you have variables in your Lagrangian that don't have a speed. So constraint appears. So your phase space is not your naive phase space, but a constrained one. And so I need to introduce some nomenclature that is standard in Hamiltonian system that are, you have first primary constraints that are the ones that are necessary to pass from configuration space to phase space and go back, okay, to invert the Legend transform. And secondary constraints are just consistency conditions, okay? So they are not necessary to invert the Legend transform. Another important classification that is important for dynamics is the splitting of constraint between first class and second class constraint. And this splitting depends on the algebra of the constraint. Okay? So if the constraint commute with other constraint, with all other constraint up to field equations, they are called first class. And if commute up to some invertible matrix, they are second class. You can imagine that second class constraint satisfy Heisenberg-like algebras. Okay. So yeah, so this is what I explained. So the basic reference for all this subject is the lecture on quantum mechanics by Dirac. So Dirac conjecture. So this in this book, what he literally wrote is this, okay? So I think that it may be that all the first class secondary constraints should be including among the transformation which don't change the physical state, but I haven't able to prove it. Also, I haven't found any example for which there exists a first class secondary constraint which do generate a change in the physical state. So maybe I should say first that the idea is that the first class constraints are gauge symmetry generators. Okay, second class constraints are not gauge symmetry generators. So it is kind of clear that first class constraints are source of gauge transformation, so though there are some subtleties. But what Dirac conjecture is that also the secondary first class, the ones that are consequence of primary constraint, are also symmetry, information on a state or fields that are unphysical. So this is the precise statement of Dirac, okay? But this kind of, in the literature, start to degenerate from the original book of Dirac, and it is adopted sometimes in a second form. The secondary first class constraints are symmetry generators. So Dirac say that generate transformation on a state that are unphysical, but unphysical is a bit more wider than what the meaning could be. Okay, so some confusion appeared in the literature. I was also confused for a long time, but I arrived to this conclusion. Okay, so Dirac is important to keep in mind what Dirac literally said. So in several references is now a standard, this second form, okay? And this second form leads to a conclusion that the number of gauge fixing conditions that you need to determine the system is equal to the total number of first class constraints. So as a consequence, it is said like this, the gauge strike twice. So it's like for every gauge symmetry, you have to eliminate or remove from your physical state twice the number of first class constraints. So this also, the consequence is a kind of universal way of counting degrees of freedom. Okay, and I started to study this because there are systems in which this is not true. So so I was thinking with my collaborators, like that the Dirac conjecture fails. Okay, it's not true in general, but we understand why. Okay, so well, so this example that I'm showing this system are example of system where the second form of the Dirac conjecture doesn't apply. So, okay, so I will just show. So, well, there are further references that where, for example, this paper by Castellani that shown that the true gauge symmetry generators, formal analysis, are linear combination of primary and secondary constraint, first class constraint. Okay, so these are, you can prove in general that these that are the only symmetry generators. Okay, so the second form of the Dirac conjecture is definitively wrong. Okay, but it doesn't say anything about the physical or unphysical kind of the fields. Okay, of other fields. So, well, in some paper, I understood that the secondary constraints are just initial conditions. So they impose restriction on the initial state. Okay. So let's say they prepare the system in some initial state. This is the function, but they are not necessarily symmetry generators. So, for example, in electromagnetism, a secondary first-class constraint is the Gauss law. So the Gauss law is just an initial condition because it doesn't depend on time. But the conjugate variable to the Gauss law is the longitudinal mode, the spatial longitudinal mode of the vector field, the gauge field, which is unphysical. Okay. But it doesn't mean that it's pure gauge. It just doesn't propagate. So in this sense, it's unphysical. Okay. But it's important to keep the terminology because in this system that I will show here, that are first order, the conjugate variable to the secondary first class constraint propagates. So there is when it comes important. So I will show this. So, well, from my Lagrangian that I started before, I defined the momentum variable in the standard way to derive the Lagrangian with respect to the velocities. And here is where you see the appearance of constraints, you see. For example, the theta doesn't have a moment. So it's a constraint. Pi theta equals 0 is a constraint. The momentum of pi lambda is another variable, is z. So this is also a constraint. And z doesn't have momentum. So it's another constraint. So these are my primary constraints that I should remember later. And the splitting here is easy. Chi1 and Chi2, that are the constraints that derive from here and here. They form a second class pair, and pi theta is a first. So the Poisson bracket for Grassmann odd variable when you have set 2 grading is just this. And here where you see that the second class constraint that chi is a second class constraint because they form an invertible matrix under Poisson bracket. And this matrix is invertible. So this is the characteristic of second class constraint. And pi theta is a first class constraint since it commutes with all the other constraints. Okay, so my canonical Hamiltonian is just a function of theta and z, if I understand that way. But I had to recall my primary constraint. And this defines the total Hamiltonian. So here I add Lagrange multipliers nu and mu to source the constraint. The observable evolves in the standard way. And my field equations in the Hamiltonian form are now this, okay? So the consistency conditions, and these are the secondary constraints, are just the stationary condition for my constraint. So for pi theta, it implies that Z is also it must also vanish. So this is another constraint. And the consistency conditions for the second class constraint determines the Lagrange multiplier. So this is another characteristic of second class constraint, that the Lagrange multipliers are not undetermined, okay, are determined by the field equations. Opposite to the Lagrange multipliers of first class constraint, which are not determined. So they are source of time evolution ambiguities, because you have a Lagrange multiplier in the Hamiltonian, you have a function that is free. So this is a gauge through gauge ambiguity. So we have a gauge symmetry in the Hamiltonian level given by this transformation together with the transformation that we saw before for theta and lambda, plus this, and we can check invariance of the Hamiltonian action. So we have also a secondary first class constraint that is pi lambda. So I have one primary first class constraint and one secondary first class constraint. Sorry, and the generator of the gauge transformation is the Castellani chain, and here dot was latex command, so it's just the derivative of epsilon times pi theta, this generator, plus epsilon pi lambda, and this is the true gauge generator. So as you see, independently, pi theta and pi lambda, which are first class constraints, are not gauge symmetry generators by themselves, separated. It's their combination which generate a gauge symmetry. Okay, so now I can I can remove from the phase space pi zeta and zeta using the second class constraint, and I have to use the Dirac bracket to do that. And under the Dirac bracket, defined like that, the basic structure that I have to that appears is this basic canonical commutation relationship. Only in the system it remains theta pi theta and lambda pi lambda. And the reduced Hamiltonian, it means that I'm evaluating in the surface where the second class constraint vanished, the Hamiltonian reduced to this expression. So there is theta pi lambda pi theta, and one Lagrange multiplier remains. That is the Lagrange multiplier associated to the primary first class constraint. So the Hamiltonian field equations, in the end, they reproduce the Euler-Lagrange dynamics. So I recover the dynamics from the Lagrangian. So this always happens when your dynamics is given by the total Hamiltonian. Okay, so basically on the surface of the second class constraint, yes, sorry. So if I fix the gauge here, the reduced Hamiltonian becomes the Hamiltonian of the Fermi harmonic oscillator. Okay, so this is a standard, but I should recall my constraint pi lambda. So the system that I described is like the Fermi oscillator with one initial condition on the system. So it's like a projection of the state of the Fermi harmonic oscillator to one subspace. So you can see this because the solutions of the Fermi harmonic oscillator in general are, you have two field equations for lambda and pi lambda, and the solution are just given by this exponential. But now if I demand this constraint by 0, I'm only left with lambda. Okay, so quantization. So the idea is how to quantize the system. So in this by now famous book, Teitelbaum, quantization of the system, in some page, that is like page 19, they argue that there are systems where the Dirac conjecture is non-valid, but you cannot quantize this system, okay, because there is no Poisson structure. They argue that. So they show one counter example, and after that counter example, they say, okay, since these systems are anomalous, since now on, we will assume that the Dirac conjecture is generally valid. Okay? So, and this is important because we all use this textbook and we just apply it. And then you go to quantize some complicated system, you just use the technique. But if there are subtleties or the system is special for some reason, like gravity, maybe what you are doing, assuming the Dirac conjecture in the second form, maybe may produce the loss of degrees of freedom, which is very important. It means that you are not analyzing your system correctly. So in this example, I show that the quantization is possible and not inconsistent. So what we want to quantize is the Poisson algebra of lambda by lambda, final representation for this. So up to ordering, the Hamiltonian is this. Then you write the Schrodinger equation, and then you find what are the stationary state, and then you solve the stationary Schrodinger equation, and then you solve the recover the time dependency, and you find it. Okay. So this is well known for the harmonic oscillator. Fermi harmonic oscillator, you have only two states, and these are the eigenvalues of the energy. But in this system, we should recall this condition, which then fix the state to be in, one of the state doesn't satisfy so this condition now remove one of the state, and you are left with only the lowest energy state of the fermion harmonic oscillator. Okay, so this system is more or less simple, but now I can do something else and write the same style of Lagrangian, but now introduce more structure, and now Z, psi, and theta can be spinors in D+1 space-time dimensions. And now this is a field theory, but the analysis is quite analogous to the former one. So the field equations are quite similar, just a gamma 0 appears here. Z, remember in the previous description, was an auxiliary variable. Here it is also an auxiliary variable. You have a gauge symmetry that is quite similar to the previous one, and Z is invariant. There is also time reparameterization invariance, and the action has a larger symmetry than Lorentz, okay, because you have diffeomorphism in the time. So this is larger than Lorentz symmetry. Okay, but if I do a gauge fixing like this, okay, theta is proportional to psi, with C with units of speed, which is the speed of light. I recover the Dirac equation. Okay. So the system is more complicated than a Dirac field. It enjoys fermion gauge symmetry. Well, it enjoys this fermion gauge symmetry and time reparameterization invariance. but the degrees of freedom are equivalent to the ones of the Dirac particle. So again, I do the canonical analysis. The structure of constraint is quite similar. Now my Poisson bracket is a little bit more complicated because I have to integrate here in spatial coordinates, but it's essentially the same. Again, I have second class constraint and one primary first class constraint. Now the Hamiltonian reduced to this form. Before it was only Z times theta. Now there is this. This is the spatial part of the Dirac operator. And now I write the total Hamiltonian. I introduce Lagrange multipliers mu and mu. It's quite analogous to the other. Okay, so if you understand the other problem, this problem is straightforward. It has just more manipulation of indices. So again, I have my consistency condition, and it appears this secondary first class constraint that is like the Gauss law for electromagnetism. And the consistency conditions of the second class constraint determines the Lagrangian multipliers. And again, as we did before in the Lagrangian formulation, if we fix the gauge, then we recover the Dirac equation. And this also, when you fix the gauge, also you determine the Lagrange multiplier for your primary first class constraint. So for a general function in this Fermi space, the evolution is given by this, and you have this constraint, okay, that is on the surface of the second class constraint. You are left only with this constraint that is again an initial condition. Okay, so I think I went very quick. So now, how did I arrive to these problems? It's because in reality, what we were doing with Jorge Zanelli, we were working in this kind of that we called different kind of supersymmetry. And we found a problem or a contradiction with the standard literature. Is that in our analysis, we found a spin half particle in the Rarita-Schwinger system, the massless Rarita-Schwinger system, which is important in the formulation of supergravity. So if you read the literature of supergravity, there is no spin 1/2 in this action. So we had a huge contradiction with the literature, and we didn't know why. So we had to see really the detail of this system, and we understood what happened. And it's related with this second form of the Dirac conjecture that is generally assumed. So now this system, maybe is the system before are not evidently connected, but with this master Rarita-Schwinger, but are very connected. So this is what I will show now. So in the massless Rarita-Schwinger action, which is not the original Rarita-Schwinger equation, the original Rarita-Schwinger equation contains a mass parameter, but anyway, we keep calling it Rarita-Schwinger action. So it's a vector spinor field. It means that it's a spinor field with a vector index, additional vector index. It's a first order action. And here I take this, the Lagrangian, and I split in time and space indices, okay? Which is necessary to do the canonical analysis. So to split and see what are the real degrees of freedom contained in this field, we introduce some projectors, operators that are this quadratic form. So this is just a composition of the identity acting on vector spinors, okay? Spatial vector spinors. And so an I, for example, is gamma I Dirac matrix minus this derivative with the inverse spatial Dirac operator. So here there is no problem to invert. Okay, so there is formal expression. It's like a green function. So these variables satisfy these identities, and then this allows you to, again, this is the composition of the identity. So I can now decompose the spatial part of the vector spinor of the Rarita-Schwinger field in 3 sectors. Okay, this is psi I, Z, and lambda that are obtained like this. Okay, so yeah, so if I use this projection and this splitting of the field of psi I introduce it in the Rarita-Schwinger action, it is split like this. So you have like a psi 0 field times Z part lambda Z dot. Here is like the Dirac action for this psi field. And you have a Dirac term for Z. Okay. So in the field equations, you get this Dirac equation for this field that psi is called double transverse because it satisfies two conditions. It's transverse with respect to gamma I and it's divergent. So this state is the one that describes the spin-spin half sector of the Rarita-Schwinger field. And you can find explicitly in this paper. This is the same year when supergravity was formed, so was immediately found. And in this paper, one of the first that said that the spin half it doesn't exist. Okay. The thing is that now with lambda equal psi, if I call psi equal lambda and psi naught equal theta, we recover from this equation the field equation of the previous section. So here there is contained a spin half. I could do the analysis again, but trust me that is the same analysis that before. Okay. So we have our analysis say that we have a spin half particle and a spin 1/2 particle. So why it was missed this in this analysis? So the reason is this, that assuming that the Dirac conjecture is valid in the second form, the spin 1/2 sector is pure gauge. This lambda field is pure gauge. So you can remove it. And the reason is that there was this secondary first class constraint that you say, okay, according to Dirac conjecture in the second form is a gauge generator. So the conjugate variable in phase space is pure gauge. So I have to remove it. It's so simple. It's a direct consequence of the Dirac conjecture in the second form. But as we shown before, this is not true. It's not completely true. And so this in some the canonical analysis in this paper, in all this paper, they just apply the Dirac conjecture in the second form, and there is no spin 1/2 degree of freedom. But we did this analysis seeing the subtleties in the Hamiltonian analysis, and we found this spin half here. So the last thing is that the projection of the Rarita-Schwinger action to the pure spin half sector is a bit different than the action that I described for the spin 1/2 particle in this term. Okay, so there is an additional term that is this Dirac term for Z, but the field equations are the same, are equivalent. So they describe the same on-shell physics, but the off-shell physics, which is important for quantum mechanics, we don't know. yet. So this is something that remains to be analyzed. And the other difference is that the spin half sector of the rarity Schwinger is not time reparameterization invariance because this term. Okay. But they are equivalent functions. So this result is potentially important because it suggests that in supergravity, there may be another particle, a spin half particle that maybe it was missed. And the consequence can be of phenomenological type because if there is a spin 1/2 particle on supergravity that is around, maybe we will detect it. Okay. So, but we haven't studied this, just that thinking about possible consequences. And so conclusions, final remarks. The Dirac conjecture in its original form may be correct, okay, up to the ambiguous meaning of what is unphysical. So I don't like much the word unphysical because I just see mathematics. So then later, I don't know in what sense could be unphysical or not. Something, for example, could not propagate classically, but it can affect the quantum mechanics of the system in the path integral. We don't know. So I don't like this word, but the original form of the Dirac conjecture may be correct, you know, with the appropriate definition of unphysical. But the second form, which say that the secondary first-class constraint generator is not true. Okay, and this was proved by Castellani already. It's just that there are a lot of confusion about what I explained. Was the real Dirac conjecture? Okay? So, but keep it in mind. And so the second form of the Dirac conjecture may lead to a ground counting of degrees of freedom or elimination of degrees of freedom if you gauge fix, because gauge fixing conditions are external conditions. We impose gauge fixing condition. The system doesn't impose it. So if you have an argument that tells you are allowed to impose this constraint as you want, then you are doing some things arbitrary. Okay? And so this is a human input in the system, which I don't like much. But the consequences are important. So in electromagnetism, it's a system of second order differential equations. So I think that probably the distinction between the first or second form of the Dirac conjecture doesn't affect the physical result. But for fermion system, which are first order system differential equation, they may affect the physical. This is the example that we saw. And the elimination of the spin 1/2 sector in the master rarity Schwinger action is consequence of the second form of the Dirac conjecture. And so the important question is, does supergravity contain also a spin 1/2? That would be very important to figure out. Thank you.
Thanks, Maurizio. That's a very, very stimulating talk. I have perplexed something. In Riemannian geometry, to have a diffeomorphism invariance, you introduce a graviton, which is elicited 2. In your system, you prove already that you have a spin 1/2 particle, which is a diffeomorphism invariance. What about in this one dimension the role of the graviton?
Actually, I was thinking, I think that it is probably trivial gravity, but I'm not sure. I haven't proved this. It's a very good question. Is if you take gravity and you reduce just the space. I mean, you remove the space and put 0 everywhere. What is the action that you are left with? Honestly, I don't know. But well, since already 2+1 dimension, the general statement is that gravity does not have propagating degrees of freedom. So I suppose in 1 dimension, it also applies. But still, I will check explicitly what happened. Maybe what we get some interesting problem also there.
What Aizawa presented, because in gravity, in the Hamiltonian formalism, the Hamiltonian is 0. So if you have a supergravity, then you have Q² equals 0, which means that you reduce your system to a topological theory.
This is one of the conceptual problems of quantum gravity, is that the Hamiltonian is 0. So in system where you have time reparameterization invariance and more generally reparameterization invariance, the Hamiltonian is 0. So it's like the conceptual problem is that then is what is time, because evolution in what? So this is very subtle, because then question appear like the meaning of time, evolution, and the counting of degrees of freedom. But so these problems were made to understand that difficult question exactly. But the Hamiltonian vanishes on shell, but it doesn't mean that it does not produce evolution, because the Poisson bracket with the fields can be different from 0 also. Now you can make the time reappear. There is a technique that introduced Kukar. I don't know the name, but it's Kukar. I read some paper. And you can recover some kind of time evolution, but then discussion start and fight start between different groups about if there is time or there is no time. So these are conceptually complicated problems, but the simple problem that I propose are toy models to understand this difficult subject.
Congratulations for your work. It was really nice to see. My only question is, when you say that you fix the gauging, you lead to some consequences. Have you tried test other gauges or a different process that give you a different gauge and test your theories?
Yes, if you use other gauge, the system, the two systems that you obtain are equivalent. For example, in the spin case, you can change the speed of light for a time-depending speed of light, but both are so if you choose the speed of light constant, it looks like a different system, but there is a map between the two that is just a transformation in the time parameter. So you just to reparameterize the time and you get a function that connects the two systems. There is one more complicated situation, that is when you choose nonlinear gauge fixing. So you say like one of your coordinates in phase space is a polynomial of the other coordinates. You can also do that. And then there may appear Gribov ambiguities. I haven't studied this. And these are important in the quantum theory because it changed the renormalization of the system when you do it. So yeah, so this is, I'm also in the future I will study that, but these are the different two situations that I spot using different gauges. Thank you for the question.
So there is a lot of things to think about after this talk. So maybe question appear after. Let's say, speak again. Next speaker is Luisa Miranda. She's PhD student in CBPF, and she will. The title of her talk is Cellular Automata Model for Herpes Simplex Virus HCV.
Hi everyone. Hi everyone. My name is Luisa, and I'm going to present about my research in my master's degree, which is automata model for the herpes simplex virus. The summary of my work is introduction, methodology, results, conclusions, and bibliography. Introductions. There are studies registered of HSV since 3000 BC on Sumerian tables. Pockets registered this virus and the herpes because the form of the lesions in the skin. But there are a lot of studies this virus, but still there is no cure. And in my work, I study the two types of the virus, ASV1 and ASV2. The transmission of the ASV1 is predominantly oral, and the transmission of the ASV2 is predominantly genital. Epidemiology, the prevalence is around 90% for the ASV1 and 20% for ASV2. The virus are distributed worldwide. Infections happen about 32% in childhood and with ASV1, and about 70–80% in adulthood with ASV2. ASV2 is more transmissible, sexually transmissible. So how the virus behave in the body? The ASV must be contact with the mucus of the skin to infect the epithelial tissues. The type of the infects depends of the immune system, the host. ASV is asymptomatic in the most population. They have like to cycle, and the transmission is cell to cell. Is more transmissible if the presence of the lesions. So after the infection, after the infection, there are two possibilities. So one, like replication, where the virus translation and the transcription of the viral DNA, and latent, where the virus stay in the dormant. After that, there are transmission and the cell death. Clinical manifestation. In the majority population, X can be asymptomatic, but in some people there are clinical manifestations and be even fatal. Some of these manifestations include ulcerations in mucus, bringer, fever, pain, and burn. So, mechanism of persistent infection. After the virus infects the epithelial tissue, the virus infects of the uterus, and there are transported by the microtubule to the nervous system and establishment of the latent. During latent, the virus installed itself in all glands. In ASV1, the installation occurs in the trigeminal gland in region, facial region, and in ASV2, the installation in the sacral gland in genital region. Latent. Latent is the period of the dormance of the virus. There are three stages: establishment, maintenance, and reactivation. The reactivation mechanism. The virus is the lifelong infection. The virus really episodes symptomatic and asymptomatic for this episode occur when the virus is the central nervous system. There are reactivation. The occur productive infections in epithelial tissues when the host immunity not awakened, occur acute infection. So when the immune system responds, they are already recognize the virus return to the latent sensory neuron. Então, so essential to fight the virus, the fight the group ASD1 and ASD2. And they are part of the immune system. In my own, I use the cellular autonomous model created by Neumann. There are elementary cellular automaton. On one dimensional, there are usually binary system. There are two states, one or zero. In my work, I use two-dimensional cellular automaton. I explain more in the binary. There are two intrinsic components of the automatic, cellular automatic model. The active there is a network and the time. The root the time. The site there is the I will explain up. And this state control the neighbor of the site and the evolution of the system. This some articles that I use in my work two of ASP and one I8IV. So in my work, I use three networks. At the first network, epithelial cell. There are three stages besides the epithelial cell. Health, C equals 0. Effect, C equals 1. Death. The second network is the stem cell. There are three stages. Empathy, C equals 0. Stage 2 not recognize, C equals 1 to -1. And the stage is recognized, C equals Z. Z is the time, detection time of the virus. The third network is the virus. There are 9 stages. Stage 0. No virus, V equals 0. Stage 1 to 8, like cycle, V equals to 8. Initial setting. First network healthy cells and only one infected cells. Second network, all empathy free. And third network, only one site occupied by the stage 1 virus is under choice. Rules. O update virus network, update the epithelial cell network, update the T cell network. Is the rules with my work. The virus network groups. If the site is in occupation, stage 1, or stage I, it's moved to stage I plus 1, I between 0 and 8, the virus ends in the cycle, logical cycle from V equal 1. If the site is at the stage 8, it starts an avalanche process. The virus energy is expressed is the coordinates in cascade and to pass to stage 0, no virus, and the neighbors of the network to pass to stage I plus 1. If the enable the site of the avalanche, it has its correspondent in the first network of the epithelial tissues, the dead stage, the stage doesn't pass to I plus 1. If enable the site of the avalanche has its correspondent of the second network defense in the stage that the cell, T cell, recognize the virus, the stage don't pass to I plus 1. Epithelial cell network rules. If the third viral network decides that speaks directly to the first network is at stage I between 0 and 8, cell becomes infected and enter this logical cycle. If in the third network decides that connected directly to the first network site suffers avalanche I equal 8, the previous step, the cell becomes dead. If the first network, the site, is in a dead state, it has a press. Probability of regenerating and becomes a health state. The probability of regeneration in biological sense means probability by born a new cell. The first cell network rules. If the first network epithelial the site is an infected state and connected directly to the second network site, the site in the second network is now occupied by T cells that do not recognize the virus and with a probability equal to the equation. The site of the second network is occupied with a T cells that do not recognize the virus, then after a period passes to recognize. Posterior infections groups. It's the same, the primary infections, but now the body is already recognized the virus, so the time of detection is shorter. Results. In the first results, we found in human system. The number of the sites is L equal 100, and the probability of bind and for a new cell is 0 in figure A and 90% in figure B. It's possible to observe to the healthy cells decrease when infection occurs, and the dead cells increase. So, but in the figure B, the death cells is greater than the dead cells. It's occur because the infected cells infects the cell, a newborn cell in the site with infected cells it will be infected too. If it infect. In here, born a new cell, the neighborhood interfere. So the new cell is infected too. Is this simulation not that these health cells is no grow is mean the host is dead in this case. This simulation represents the begin the virus ASV with humans when it is not symbiotical and the person infected is dead. So here is the simulation with T cells and the time of detection Z equal 50 and 500. It's possible to observe the variant Z, the density of the T cells grow, and the timing of detection here is shorter than here, and so the infection in here is less aggressively in here, but the response of the body here is more is greater here. Here is the same is the simulation for time longer, 30,000. So Z equal to the another graph. Z equal to this graph is the primary infection. So here there is other infections. There are primary infection. After that, the humans immune system decrease, and the other infection. But now the time of detection of the virus is different because the bodies, the cells already recognize the virus and they fight with them more quickly. So in my work, I create this rule, the cell automata for the F viral. In code in Python, I simulate this rule. In no immune system, the virus compare aggressively and the causing death of the host. And with immune system and differently, it's possible to observe different infections when the short infections is less aggressively. It's the rate, the infection is more aggressively, but the response of the immune system is greater too. The infections is the timing of detection the virus is different in posterior infections, and the body is recognize the virus more faster, and it's it. Thank you.
Em português ou em inglês? Ok. Ali você colocou no gráfico os tempos, mas qual é a unidade? Então, ok.
A unidade de tempo do meu trabalho ela é adimensional. No entanto, quando você estuda pela literatura, você pode observar esses picos aqui, eles duram em média, no corpo humano, eles duram em média 2 semanas.
Thank you. Interesting talk. I don't understand. Can you go to the other page of results? Yes. The other one there. Yes. I missed what are these parameters, L and P res.
L, number of the sites. Remember? No, yes, number of the sites. Is occurring the rule is equal 100. Represented the area of the infection. No caso, em caso de ASV1, oral region, and in case of ASV2, genital region. PRES é the probability de born new cell in the area of the infection. There is area infection, but the is being born a new cell after the E these parameters is no, because the rules change. The rules change. This rules is rules for X virus. If I work in another virus, that is different rules. The rules. Yes, but modifications in the use the rules, but for example, HIV, their rules for HIV is not the same as rules HCV. Yes, yes. The primary, the first graph is the value if the first contact with humans. The virus virus is with humans a lot of times. So the last time eles ficaram quase simbióticos. Yes. But antes, before the virus is killed the host.
More questions? More questions? Okay, I have a comment. Can you show me, please, it's next page? This is a kind of philosophical conclusion. You see, when the number or stage of immune system to react is short, immune system recognize it quickly, but it is not strong reaction. Yes, this red is not so high. But if immune system is a little bit delaying in recognizing, the reaction is better. So means like immune system take a time to even without reaction, but takes time, and then a response is good. So it is like advice to life: don't be in a hurry. So, one question more.
This kind of study, do you send to health agencies to provide some input, which kind of action can be taken, which time? Esse tipo de estudo com célula autómata é utilizado pela agências sanitárias para tomar atitude, decisões, como intervenir. Não?
No questions? No?
No caso de algum vírus que, como exemplo, se você quisesse introduzir uma vacina, o que modificaria ali? As regras. Não seria só mudar o tempo de reconhecimento, ele colocar 0.
More questions? So I think it is great to have talks which enlarge our knowledges and the applicability of mathematics and physics. Thank you very much. Let's thank the speaker. We have a lunch break till 2 o'clock. Yes, or 2:15. Till 2 o'clock. Let's. Okay, let's. No, 15 it is something not respectable. Okay, so 2. Okay, here.
Can be respectable. We will start at 2 p.m. cum tempore. This is the German to start 15 minutes after.
My talk. I
Fala? Não. Baixou, baixou, baixou. ¿Cómo? A ver, así, ¿no? Un poco menor. Entrou, muito obrigado. Opa, opa. Maurício?
Don't sleep, please. I will keep you awake. This restaurant, because it's a so there is no restaurant now.
After there is a Academy of Science Brazilian. They have
Mm.
Que parece que está todo. Para ver, no.
Por onde que eu abro ele? Embaixo? Is it? Som. Tenta lá da frente para ver se chega.
Teste. 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 Tá. Porque eu acho que a mensagem tinha.
So welcome to the afternoon session. Please keep awake, open your eyes like this big. It's a pleasure to present Jana Kuznetsova from Federal University do ABC. She's going to present her work on set2 cross set2 graded algebras and superalgebras and invariant physical models. Please.
I know that. Thank you very much. I think a workshop is for me is interesting, and I would like to present some simple results of some introduction to the integrated models, how different they can be, and some result obtained with my master student Lucas Vasconcelos. And I wanted to present other result of the integrated superalgebras. But partly this result have been presented by Professor Aizawa because it is joint work with Professor Aizawa, his student Ren Ito, and Francesco Toppan. So here I will maybe not skip, but will go quickly and present all these things. So the presentation is based on three works. Two of them are published. One is with Francesco about classification of minimal algebras. Second one, it is presented physical model in the integrated Lie superalgebra. And last one is a work in master thesis with Lucas about a completely different structure, which is not superalgebra, but algebra, which is not investigated in literature. So here I will repeat that we will discuss the integrated supersymmetric systems. Inspiration of creation of graded systems is by symmetry between two kinds of particles, bosons and fermions, and they can accommodate in one algebraic structure, which is called algebra, superalgebra. And Rittenberg and Weiler were discussing how to accommodate also colors of quarks, and there should be more grading spaces than two of them, one bosons and three different. How to accommodate colors. They didn't succeed, but they created a huge class of algebras which are with graded Lie algebras. And class is higher than the two graded because grading group, the two graded, the two is grading group, can be take any abelian grading group. But here I will discuss two systems, the two graded superalgebras, which has bosonic part, two parafermionic subspaces in one exotic bosons, or the two graded algebras, which contains only bosons and three kinds of exotic bosons. They are different. And about words, I will use word color or word graded, which as synonyms in the talk. For example, Lie algebra has one graded spaces, superalgebra two graded spaces. And if I have grading group, in principle can be infinite, can be finite, can be infinite countable, like n natural numbers or integral numbers, or can even with cardinality the more than natural number continuous group. So the construction does not show any difficulties, not difficulties, but contradictions. So, and an algebra is divided as a direct sum of gradient spaces, and number of spaces is a number of elements in gradient group. For example, if I choose gradient group these three contain 9 elements. So if I will consider these three graded Lie algebra, it will contain consist on 9 graded spaces. So you can even it can be very simple. For example, if I have matrix 4 by 4, I have 16 elements. I can tell that it is 16 graded spaces. as vector space, because in vector space we have only sum. But if we have multiplication, so we will have less number of graded spaces. What is the general properties of this? Associative graded algebra can have grading, but we will consider algebras, which Lie algebras, they have some symmetry properties. For example, J alpha, J beta equal -1 power this product, J beta, J alpha. So symmetry properties of graded Lie algebras, color Lie algebras, or graded Lie algebras are encoded in this power of -1, which is scalar product between element of group, of gradient group. And scalar product should satisfy two conditions, this condition and this condition, associativity and gradient commutativity condition, where these R and S, they are integer numbers. So we had a lot of spaces, and now we go to a particular case where we have, but you see, in any, it can be some square, third, fourth order root of identity, but we will work in Z2 graded structures, and but even for any of them, diagonal element AA plus AA, it is an integer number. So it diagonal product, it is commutator or anti-commutator because we have integer number. So, and then we have classification. If all diagonal product, as has Ricardo said, is commutators, we call it colorly algebra because we do not have bosonic, fermionic subspaces. If at least one diagonal product is anti-commutator, we call colorly superalgebra. So let's repeat. If we have Z2, the algebra or superalgebra is divided in 4 subspaces, and there are 2 different definitions of scalar product: anti-commutative, commutative scalar product. If scalar product is anti-commutative, this is a table of commutation and anti-commutation relation. And this is colorly algebra because all elements in 0, 0, 0, 1, 1, 0, and 1, 1 sector, they are commutators. So inside of any sector, particles see each other like they are bosons. But if a particle from one sector meets particle from another sector, 0, 1, for example, with 1, 1, they are fermions. So it is like they are like to each other. With they are brothers, they are the same bosons, and for other sectors, they behave as fermions. So we have each sector 0, 0 with 0, 1, they have Lie algebra. Lie algebra is a subalgebra. 0, 0 with 1, 0 also Lie algebra is a subalgebra, and with 1, 1 also. For graded superalgebras, we have another product, another type of commutators, anti-commutators, and 2 sectors are like fermionic, but we call them parafermions because they commute one sector with another commutators. No commute, no, not commute, but product is defined as commutator or anti-commutator. So, so 2 different structures, and this structure is well studied because it is a nice, you can see this like generalization of supersymmetry. For example, 0, 0 with 0, 1, this square of commutators, it is commutators, anti-commutators of superalgebra. The same with 0, 0 with 1, 0, commutators and anti-commutators. But between sectors, we don't have anti-commutators, we have commutators, so it is generalization. And this was studied well in literature, and there are a lot of open problems and questions to address to. Then, you know, when you study algebra in mathematical department, there is at the beginning a chapter, low dimensional algebras, to understand what what is important to analyze differently algebras. So we decided to analyze low dimensional Z2 color algebras. So we define that minimal dimension is 4-dimensional, and in each subspace we will have only one element, but also there is no subspaces without element. So we call it minimal algebras, and we want what kind of commutators and what kind of structure constants can appear, can be admissible to satisfy Jacobian identity. So how it constructed? Q1, Q2 result should be in subspace which is sum of 0, 1 plus 1, 0. Result should be in Q3. So this is decay structure constant. A modulo of completely antisymmetric tensor, it is only, it is not important if it's 1 or minus 1, important that it will not appear Q1, Q2, it will be only Q3. And here is also, so we have D1 to 3 and B1 to 3 structure constant, and you create a lot of Jacobi identities, HQ1, HQ1, Q2, and have a system of 9 equations or more, and then to resolve, to have a possible, to analyze a possible solution of the system, you have different minimal algebras, superalgebras. This is result of classification. You see here, we have 2, epsilon equal 1 or minus 1. Here we have 2, 2, 1, on 1 A5. This is infinite number parameterized by parameter X. And here it is infinite number of algebras parameterized by parameters Y and Z. So for me, I will present result for this algebra, A1, with epsilon equal 1. And here, this is interesting, even more interesting. I don't know why we don't choose this, because it is a computation are easy and it looks more like SL2 in some sense. But result is here. So for minimal superalgebras has been done the same. We call Q1, Q2 fermionic part, Z a generator of 1, 1, A generators of 0, 0. We have more structure constants. For example, Q1 is fermionic, so you should have anti-commutator Q1 with Q1, Q1 squared. We have this structure constant. And in this minimal superalgebras, we have 21 particular case. And here they don't enter 21st one particular case. And we have this. Where are generalization of super Poincare? They are case 10 and case 7. They are generalizations of super Poincare. This from 1 to 6 some restricted cases, and from 11 strange algebras, which I will show you before, which you have HQ1 equal Q1 and Q2 are eigenvectors of H operator. Opa. So, no. They are eigenvector of H operator. They are interesting algebras. I think 21 case appeared in the last discussion about integrable systems. But it does not appear here on the transparency. So one-dimensional graded super Poincare already has been presented in Professor Aizawa's talk. So this is definition. This is I will quickly go here, because first we tried to look as imitate this construction to the two gradedly algebras. So there is no, as I know, I don't know any paper on physical system of parabosons only, without parafermions, graded bosons. So we decided to do it, and we tried to imitate this process. We tried to present generators of our algebra as operators which act on group manifold. We have group manifold with graded coordinates. They satisfy abelian because they are graded superalgebra, and coordinates simply are relation between them are abelian. This is changing of group group element by acting on infinitesimal element, and then we have modification of infinitesimal modification of delta x. X is a set of coordinates, and here it is representation of the algebra by differential operators. And here are covariant derivatives for to construct action, which is used by acting on superfield by different covariant derivatives. So this is superfield. I think you have already seen this in the first talk. So once more, I can tell that appear X here, which is different from super algebra, because when z squared appears, it will be z squared, 1 plus 1 1. It should be in 0 0 sector. It goes here, and it begin to have some extra coordinate x. So all component fields in decomposition, they have another coordinate, new one. And you can ask yourself, aha, maybe space is created by the 1 1 coordinate in some system. We have 3 space coordinate, real physical space, I'm telling. And they are maybe from some z1 1. We don't know. So we don't know how it's constructed, the word from our feeling. And here, what I want to present, we use matrix presentation of theta's, yes, and sectors. So 0 0 diagonal, 1 1 diagonal blocks with anti-diagonal, 1 0 and 1 1 anti-diagonal blocks, diagonal anti-diagonal. Now we can tell, this is not general. This is general because it is one-to-one correspondence. If we use matrix without different entries, only with one entries, and it satisfies correct relations, you can substitute theta's by matrices. And you can even vice versa think about matrices when you see theta. To computation with theta's are easier because you don't need to write down matrices, but it is the same. So then this is substitution of Z2 graded space coordinates by matrices, and then appear Y. Y is a coefficient and matrix in matrix M3. So this is connection of matrices. I will not tell much about them. And there are component fields are also can be presented by matrices. Why matrix appear in coordinates and also appear in component field means the following. You have a field, but field should anti-commute, for example, with for example, anti-commute with 1 1 field. How it will anti-commute if you have only functions of 2 variables? It will not anti-commute. So, but if you multiply by matrices, it is like to input commutation rule, not commutation, but symmetry in change of particles rule. You put using this kind of matrices which satisfies right properties. So super function has this phase, and we have Lagrangian, which is covariant constructed by product of covariant derivatives by one element minus some function of superfield. So this is a result in Lagrangian and kinetic potential part. Mamma mia. Okay, it is green. Here it's I have black. So from action, it begin to be invariant not only this four-dimensional the gradient algebra, but appear one more dimension between two coordinates, one mu y and second t time coordinate. And here Lagrange equations. We have different Lagrange equations if we define different prepotential phi. Yes. So this is conserving current. And there are some remarks about two-dimensional relativistic model. And for me, is important that we succeeded to construct this model. But for me, it's also important how, because we know how to behave Grassmannian coordinates. And we wanted to know how to behave one graded coordinate. So one graded coordinate has two rules. It creates commutation, it inputs some anti-commutation property with each of fermionic field, and also it gives more new coordinate, new degree of freedom in a physical system. And it is very interesting because what it is, yes, how we can create this. So it is really interesting model which gives some new world, yes, in some way. So here also, I think I am repeating really talk of Professor Aizawa, because this is algebra, this is new generator, and this is new generators for to close the algebra. Algebra closes, it is 1 + 1 Minkowski graded, the graded super Poincare. So if you close new coordinate y in circle, we can create a string model. Some of them are consistent, some of them are not consistent. So this is P, 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 A, P. It is periodic and anti-periodic conditions in any sector 0, 0, 0, 1, 1, 0, 1, 1 sector. And here I will show periodic boundary conditions, and we define function in periodic conditions this way, like infinite series. And here there are results. We have kinetic Lagrangian for each element in infinite series, potential term also, and Lagrange equations of motion here. So top remark that free flow closed string corresponds to an infinite set of graded harmonic oscillators plus zero modes from recovered phi0, psi0, x0. That for quadratic potential, the energy is shifted to 1, and fields no longer describe zero modes and describe energy k. Okay, to k shifted to modulo k. For arbitrary potential, invariant action produces infinite set on interacting particles. So I have 20 minutes, yes? Okay, I will speak very slowly. And then we decided to work colorly algebras, and nobody is attracted. I tried to attract a group in Japan, I tried to attract Francesco, nobody wanted. So, but yeah, really, because we don't have zero. When we have Grassmannian something, they don't have infinite series, yes? And here we have some bosons which are anti-commute. This is strange. And if this is not a super Poincare generalization, this is something something different. So, and then we took A1 graded minimal color algebra and work with Lucas. So we have First, we wanted to imitate a procedure which we did in superalgebras. So we like they are coordinates are bosonic, we call them x, y, z, and t. And t will be 0, 0, and x, y, and z are pseudo-bosonic. Actually, to call them pseudo, you cannot, because Joris van der Jogde told that pseudo means other thing. So exotic bosons. And it is a space where coordinates x, y, and z commute with 0, 0 coordinate t. And as there is a 2, between sectors, they should anti-commute. So x anti-commute with z, y, and z and y, and others are anti-commuting. And then we take A1 minimal color algebra. So we have H with all Q is 0, Q1, Q2 equal Q3, Q3, Q1 equal Q2, Q3, Q2 equal Q1. And we construct first group manifold, and then we act on this group manifold by infinitesimal action of generators of this algebra, HQ, Q1, Q2, and Q3, and we hope to produce realization of this algebra by operators which are acting of this group manifold. And then we should use Baker-Campbell-Hausdorff formula. And I can tell you this is, unfortunately, it is not complete formula. It should be plus here. I don't know why I didn't put almost the same structure, but last will be a joint action of B on A. So this is a formula. So you can, and here you should take any combination of power of A, for example, M times, adjoint B commutators, and 1 times, and other ones of B. And this way you calculate coefficient, this, and multiplying by this. So so this formula is Baker-Campbell-Hausdorff-Dynkin formula, a little bit different from Dynkin formula, but it is easier to compute these coefficients. These coefficients also not complete, should be plus something from when last is A, not B. So, but as A is infinitesimal, you see A is one of these exponents where with infinitesimal graded coefficients. So A we will not have. We have only number of B commuting with others. So formula is like this, but it is infinite series. So if we compute this, make this computation, we have realization on of operators by first order differential operators, but coefficients are infinite polynomials. Here, for 3 points, some other polynomials enter here, here, and here. For example, here I present on the slide only second order polynomial, but in second order, where is Z, it enters Z 1 minus omega, when omega is x squared plus y squared plus z squared. It is 0, 0 sector. So here will be 1 minus omega. Here it is already third order, yes, z plus x squared, z times x squared. Here zx will multiplied by 1 minus omega. And so structure is, in some sense, it is computable and repeatable. You can repeat multiplying in correct places 1 minus omega. But we can see what happened. It is realization, but by differential operators multiplied by infinite polynomials, infinite series of potentials of three variables, but it is not very useful to construct physical model. Even more, if I want to check this, so we constructed this, but we did not check commutation relations yet. But we checked up to first order. Now, up to third order, it closes with some small differences of bigger order. So hope that bigger order will close with higher order, and then it is really closing. It is realization, but it is not very much useful for physical models. So we decided to work in normal space, x, y, z, t. Here, x, y, and z are not anti-commuting normal coordinates, and we decided to what is mathematics? We have algebra. We want to have a representation on graded vector space. Vector space also should be graded. So our graded vector space is a function of 4 variables which take value in quaternions. So it consists on 4 component functions: phi0, phi1, phi2, and phi3. And grading is phi0 is in v0, 0, phi1 times I quaternionic imaginary unit is in 0, 1, times j in 1, 0, and times k in 1, 1. And realization is not difficult to construct. It closes the same A1 algebra. H commutes clear because it's dt, yes, with others, and they anticommutators Q1, Q2 gives Q3, etc. So how we construct Lagrangian? So what we construct? A Lagrangian is functional. It is function of function and first order derivative. We don't use other order derivatives. So we create function, and also we use trace because we need that action is to be. We need action to be in 0, 0 sector. So we take quadratic. I don't use here Minkowski space. We have Euclidean coordinates x, y, z, and t. And index means the phi dx, the phi dy, the phi dz. And so for trace, I use matrix representation of quaternions. Each imaginary unit of quaternion can be represented by 4 times 4 matrices using this alphabetic presentation. And so this function can be written as a matrix element in component fields, and trace is some of these, but we don't have function. We have squared of derivative and some function of v of phi, yes? So, and this model make some property. I want Lagrangian to be invariant. So if I have Lagrangian and I take trace of Lagrangian, only 0, 0 sector will enter diagonal, yes? But I use Q, which is times I. So if I have some square and I have this momenta, angular momenta around z axis operator, as this I will put in 0, 0 sector part with I. So for Lagrangian to be invariant, for 0, 0 sector enter Lagrangian in physical model, I should require invariance not of this sector, but of quaternionic imaginary unit sectors. So it is so strange model. So I should imaginary unit to be rotational invariant for to enter another thing to Lagrangian. And here is example. For example, if I have phi squared, this will enter Lagrangian. But invariant under Q1 should be this sector. It should be this phi0, phi1. And because of this invariance, phi0 should be invariant under xy, and this is not xy. This is xy. So phi0 should invariant under everything, phi1 under xy, phi2 under yz rotation operator, and phi3 under xz rotation operator. So means that phi0 should have rotational invariant, should depend only on distance from our origin. Phi1 should be invariant under x. So it should depend only on x and distance from the x. And phi2 should be invariant this way. So this I want to draw. So means phi0 should depend only on this. Phi1 should depend on this. Phi2 on y and distance, and phi3 also. I'm telling about the most general case. So we can tell them that phi0 it depends on this. It depends on x, y, z, but only in this combination, phi1 of distance and z coordinate, phi2 and phi3 this way. So and also we cannot put in Lagrangian these derivatives. It is direct computation. We saw that these derivatives cannot participate Lagrangian for this case, but derivative in rho can participate Lagrangian, can enter Lagrangian. So Lagrangian, free Lagrangian will have a form phi point squared plus phi rho squared. So trace of Lagrangian has this form. This is in common component fields. And you see early Lagrange equations are written in x, y, and z, because there is no common coordinates for each component field, but common of the x, y, and z. So means that we consider like composite function, the phi1, the r times the r, the r, the z. So it is component function computation, equations of motion. Also, you cannot exclude coordinates x, y, and z. For phi0, which depend only on rho, it is a nice equation of motion, and for other field, there are bigger equations of motion. So it is how to say formal wish, our formal wish to consider the most, not the less restricted system. But if all of them depend only on rho, we can consider a system will be simpler, and we consider different potentials. For example, for phi acute potential, we have this kind of Lagrangian and this kind of equation of motion. We have a connection phi0 is related in system of equation to phi1, phi2, and phi3 appears this way. Index rho means that it is derivative in rho. Here it is phi0 second derivative in rho. And their function without derivatives like this. And phi4, don't know why it does not enter. Sorry, but in my screen it entered. So here phi I squared and phi0 squared. Here they have more interaction. All component field enter in every equation of motion. So so it is an example of this system. What conclusion we can make from this? For first, that A1 algebra is really it is strange algebra, and I can consider this results as a result of exercise, not a result of some physical meaning. It is a mathematical structure which is invariant under the two-graded Lie algebra, not superalgebra. Other algebras, A8 is more interesting because it is like SL2. In SL2, we know physical meaning. But rotational invariant system in different directions, perpendicular, it can be applied to some, I think, practical problem with rotational invariant system in different direction. So, this is all what I wanted to say to you. Thank you for the attention.
Questions?
Jeanne, with your method, you applied to this very specific example of A1 in the list. But in principle, you could apply to any other color algebras appear in the classification. And
Eight commutators are 0. No, anti-commutators. Stop. Commutators are 0. No, anti-commutators are 0 and commutators are x, y, y, z, and 1. So if we have commutators which are not 0, we have like structure H with one element can be 1, H with other -1 will be SL2. So here we can construct it is Z2 graded generalization of SL2. And even we can have 2 SL2, one with 0, 0 with 1, 0 and 1, 1, and other, for example, with 1, 0 and 0, 1. So we have 2 SL2 organized in some strange way. While here it is really rotational invariant and nothing more, and other coordinate which does not participate. But it was interesting to see problem where to appear something in real world, something should be symmetric in hidden world. So it was really interesting for me.
Another question?
If I understand correctly, if starting from this classification and constructing this action, you can at least produce a free model or equivalent of harmonic oscillator. I mean, generalization of harmonic oscillator if you take a quadratic term in the potential, which maybe you have not yet investigated in the literature, because this system that you produce is rather strange.
In each sector, and they anti-commute between each other, there are 3 bosonic harmonic oscillators which are anti-commuting. But this we should continue to create eigenstates, and states has also a contradiction because they have anti-commute and commute, and some, if you have, for example, A1 a plus state, and it should anti-commute and can be only trivial. So we should think how to not to have triviality.
More questions?
Maybe I missed. You talked about the A1 invariant model and consider the phi squared. If the phi squared is introduced in the Lagrangian, you have some condition on the component field, right? Yes, if you take into the phi square term in the Lagrangian, you got some conditions on the component field. Yeah, that one, phi 1, not phi square. Yes. Right, okay. Yeah, right. So that condition is enough to for 5 cube or 5 to 4th.
It is interesting question. For example, if I have some power which satisfy condition in imaginary part, which is different from, which does not lead to these coordinates, this dependence. But problem is in phi point. Stop. In phi point, if I have phi point here, phi point squared, but it should be Lagrangian if you want to have the dynamics. Here will be phi point, phi point, phi point. And this, it should be invariant under x dy minus y dx. And this gives condition. So it means this square gives condition on this dependence, which leads to this. If I talk cube, I will have, I don't have here formula, but I mean, I don't care, this is a real part, yes? I don't care about imaginary part, because if I in Lagrangian already I have phi point, stop, opa. If I have kinetic term, if I have kinetic term, I already should, they already should depend only on distance, on distances in different axes. I think if I have more members, it will be more restriction. I mean, from phi point square, I have phi one dependence only on x, on distance to x. If I have third order, some other field appear here, and it should have only these conditions. And if it have distance from here, so it will be more restrictions can appear. Nothing better happened. For this reason, it's better to have only on row dependence and consider system central symmetrical system.
More questions? So in this model, what are the fields that propagate? Because what are the fields that propagate? Because all of them, because what are the fermions type of fields? But only exotic boson. And the other disappeared, the fermions. Okay. Okay. Thank you. If there are no more questions, please let's thank again. Thank you, Chena. Now that the next talk is Isaac. Yes, I think. But they need to put yes. Would you like to change the position? Yeah. I think it's better. Okay. So this is the point. Yes, this go. Okay. And can you put the first? Yes. So It's a pleasure to introduce Isaac Porto de Freitas. Did I say well? Okay. So he is presenting his talk entitled Doubling and Deformation in Graded Lie Superalgebras.
So thank you. I think that most of you must know me. So I am a student, doctoral student here at CBPF, and I hold a master's degree from this very institution. And now I'm going to talk about I'm going to present on the topics of deformations, doubling and deformations in graded Lie algebras and superalgebras. Okay, so these are mathematical tools that I started to develop it in my master studies. And these, doubling construction, I started to studying in my master studies, and this deformation in graded superalgebra systems, I am studying in the beginning of my doctoral. Okay, so I decided to separate my presentation in two parts. These topics are not necessarily related, but doubling construction for zeta-2 and superalgebra is a mathematical tool that I developed with Rodrigo and Mateus, and we expect to use this on this mathematical tool on the context of supersymmetric quantum mechanics. Okay, so supersymmetric quantum mechanics is one of the main topics of our research group. And so I think it's important to show you just a little of this. So let's start with a brief introduction to the definition of graded Lie superalgebras. Okay, so a graded Lie superalgebra is a vector space that can be decomposed into homogeneous subspaces. These homogeneous subspaces identify as gradings. Okay, so that is summation, direct summation is what it means. That is the way that I can write mathematically the decomposition. Okay, so when we are talking about Lie bracket, Lie superalgebra, sorry. The most important is the Lie bracket, okay? And the Lie bracket has this definition here. And of course, this result must be, should be an element that it's on the vector space, okay? That must be an element of the algebra. So this definition here is important because later I will present the topic of deformed Lie bracket, Lie algebras, and the deformation is can be written as represented as a change in the definition of the Lie bracket. Okay, so the mapping is operation between the gradings of the elements of the Lie bracket, and the mapping will define the Lie bracket as a commutation or an anti-commutation. Okay, I think most of you already know about this. So, well, the possible applications of graded Lie superalgebras are in quantum field theory, in theoretical models for condensed matter, paraparticles and particles theory, string theories, and supersymmetry. So in the topic of doubling construction for zeta-2 and superalgebra,
this is a procedure to construct a zeta2 n algebra by doubling a zeta2 n minus 1 algebra. Okay, and how does this work? I will take the elements of my zeta2 n algebra and project them into the even and the in the odd sector of my zeta2 n algebras. Okay, so one important aspect of this tool is that the initial algebra and the intermediate algebras are necessarily a sub-algebra of the final algebra. For example, if I started from zeta2 and I double this algebra to get a zeta2 algebra and so on and on, all these algebra, the zeta2, the zeta2 2, the zeta2 3 are necessarily a sub-algebra of my zeta2 n algebra. Okay, so let's take for an example. Let's see how this works. Okay, I think the most pedagogical way to present this is showing the matrix form of the doubling. Okay, so let's consider a zeta2 algebra who has these two generators, F0 for the even sector and F1 for the odd sector. Okay, so let's take these two elements, F0 and F1, and project into the even sector. This matrix here, sorry, just a comment. Even sector are matrices diagonal, okay? And diagonal matrices, sorry. And odd sector are represented by anti-diagonal matrices. So for the odd sector, I have this matrix here. This sign of minus is because I'm choosing for the doubling. Just a comment. The doubling is fundamentally direct product. No, sorry, a tensor product. Tensor product. Okay. So I'm using to the algebra zeta2 who has these matrices here. Identity, okay. 0, 0, and this 7 and minus 1. And okay, so when I do the doubling for zeta2 algebra, for example, F0 and F1, to construct the elements of a zeta2 algebra, I will do this here for even sector. I have G0 that is equal 1 tensor product F0, or G1 is 1 tensor product to G. Sorry. F1, and the odd sector is for example G0. Okay, and is it okay? So we can carry on, we can continue the doubling, okay? And we will get these elements here, the G of zeta2 algebra, and we can use them to construct a zeta2 algebra, okay? And the generators of this algebra is this G's uppercase. Okay, so that is the matrices. That are the matrices of even sector, and for the odd sector we have this. So let's use let's take for example, S2 zeta2 algebra, okay, who has these elements here. F0 is the Hamiltonian, and F1 is the supercharge, okay? So when I do the doubling for this matrix, I will get this algebra here, S2 zeta2 algebra, and I have these matrices, and I can continue the doubling, and I will get zeta2 S2 zeta2 3 algebra, and I get this matrix here for the even sector and the odd sector. Okay. Comment about this example is that the S2 has the structure of complex numbers. S2 zeta2 has the structure of quaternions, and S2 zeta2 3 has the structure of octonions. Octonions is and quaternions is okay for. Okay, octonions is non-associative algebra, okay, but the S2 zeta2 3 is an associative algebra. Is associative algebra, okay? So what the structure constant appears here in the multiplication between two elements of this algebra here, okay? So I can call it by this property of quasi non-associativity, okay? So we can proceed with the doubling, and we'll get this matrix here, S2 zeta2 for algebra, which has the structure constant of sedenions. Okay, sedenions is not a divisional algebra, but S2 zeta2 for is a divisional algebra, of course. So the interesting aspect of this doubling is that to construct a zeta2 n algebra, for example, starting from the zeta2, I do not necessarily need to know the intermediate algebras. Okay, I just need to know the structure of doubling, how this work, and of course the generators of my initial algebra. So, okay, now we came to the topic of deformations in graded zeta2 and superalgebra systems. Okay, here I will consider two types of doubling. Okay, the first one is the Q-bar deformation in gradedly superalgebra. Okay, and this kind of deformation is very similar to a deformation that already exists in the bibliography. Okay, the Q deformation algebra, but the Q are not the same. Okay, the definition of for example, the Libract is very similar, but not necessarily the same. Okay, and theta deformation, theta here is not the function theta. Okay, theta is an operator that I will define later. Okay, and so let's start by the Q-bar deformation in zeta2 and graded algebras. Okay, so when we are talking about superalgebra, we are talking about a supervector space, and I can define here in this space superalgebra. Okay, and the superalgebra, I can define the Lie bracket of the superalgebra as follows. In the beginning, I showed something like this. Okay. AB. BA is leg A and leg alpha B. Sorry. Okay, this is the grade for I think Sobrero doesn't know this, but this is the grading of this operator, this generator A. Okay, so what I did here, I just write this like this here. Okay, so and in this algebra, the result of the mapping, the gamma, is always equivalent to 0 or 1. Okay, so in this space is what it happens. The gamma is always 0 or 1, or 1, sorry. And now I want to consider attached to this space V, a space I here. And so that in the union V and I, the mapping is not more necessarily 0 or 1, okay? It can be a complex number. So if we are in this algebra here, and if we perform a deformation on this algebra, on this super algebra, and such that A goes to A bar, B goes to B bar, gamma goes to gamma bar, but gamma bar is equals gamma plus this complex number here. Okay, so I can write the definition of this deformed algebra like this, and we will get this result here. Okay, so this here or this here, I just expanded in series. Okay, is what I'm calling by Q bar. Okay, this Q bar is very similar, but not necessarily equal to the Q of the Q deformed superalgebras, okay? But this Q here, not the Q bar, is a value between -1 and 1, okay? And this Q bar also is a value between -1 and 1. Because gamma is 0 or 1, so this is plus or minus my exponential. Okay, so let's go. A possible application for the Q deformed algebra is the construction of a Q deformed oscillator, and here I am presenting the Biot-Darm's approach. Okay, for a Biot-Darm approach for the bosonic case, we have this definition here, this algebra. Okay, and these other definitions. So this representation for the bosonic oscillator must be necessarily unitary and irreducible. Okay, I must choose a Q that respect this specification. Okay, so if I choose Q equals Q bar, sorry. So and here for the bosonic case, epsilon is 0. So this equation here, this equation also, sorry, this Q bar here, this exponential is equal 1. Okay, and we have only this here. Let's apply this Q bar, this Q, this exponential here, in this definition 90. Okay, so we will get this NQ. NQ is the number operator, the Q deformed number operator. Okay, so using the first term of this series here in, okay, we will get this result, okay, for NQ. So, okay, and an interesting comment is the following. If I choose this approximation up to the second order, this NQ is equal N, okay? I did this calculation with Matheus last week, and we get this result, okay? And this function here that transforms the operator, the annihilation operator into the Q deformed annihilation operator must be just a phase, okay? We can see that in this relation here, okay? If NQ is equal N, this is just a phase, okay? This function F here is just a phase. So nothing of new seems to happen. But using the definition for NQ, this approximated value for NQ, we can construct the Q deformed Hamiltonian. Okay. According to the Bierdarnes approach, the definition of the Q deformed Hamiltonian for bosonic system has this is this equation here. Okay. So using the expression for NQ, we get this result for my NQ, my Q deformed oscillator, and the Einstein value for this Hamiltonian is the energy of the formed state NQ is this equation 25. Okay, so we can also construct a fermionic Q deformed oscillator, but in this case, we had to take care because when we try to, for example, we are on the Q deformed oscillator for fermions. When I wanted to go back to the non-deformed system, the Pauli exclusion principle must be preserved. Okay, so using in the place of Q, the Q bar, we have a problem. Okay, so for this analysis, we have two choices. We can choose this NQ, the Hermitian NQ, or a non-Hermitian NQ, anti-Hermitian, sorry, NQ. It's okay. For let's do the calculations for Hermitian NQ. So this we have these relations here. Okay, and therefore, if this I get this result for the anticommutation and this result for commutation. Okay, this commutation and this anticommutation is the normal definition of commutation. Okay, is not the deformed definition. Okay, so for any Q anti-Hermitian, I have this result for the anticommutation and commutation relations. So we must compare these algebras, these results, with the fermions algebra non-deformed fermions algebra. Here's a typo, okay? I wrote Q here, but it must be only B and B dagger. Okay, so if we choose the case where NQ is a Hermitian operator, I cannot recover the fermionic algebra when the deformation goes to zero. The deformation goes to zero when epsilon is zero, okay? So that, let's choose the case where NQ is a anti-Hermitian operator, okay? So we choose this case for anti-Hermitian operator. So let's analyze what happens with the relations of commutation and not and commutation when the epsilon goes to zero. This here goes, the anti-commutation goes to 1. Is what we happens, is what we expected to happen for the non-deformed oscillator. And this commutation goes to minus to the limit of NQ when epsilon goes to 0. So in order to recover the non-deformed fermionic algebra, we must define this limit here like this value, okay? Because we want this result here. So, okay, and now we want to construct the Hamiltonian of Q-deformed fermionic oscillator. And what we have, an operator NQ, a number operator, Q-deformed number operator that is anti-Hermitian. And what we needed that the states, the energy of deformed states must be a real value, okay? And we want to also recover the non-deformed fermionic Hamiltonian when epsilon goes to 0, okay? And okay, so I propose this Hamiltonian here, okay? This is this function U is a continuous approximation for Heaviside function, okay? And this Hamiltonian, when I calculate the limit for epsilon going to 0, I get this result here. And okay, and when epsilon is small but not necessarily very close to 0, so this function here U is equal 1, okay, I will have this definition for I will have this equation here for the result of this, okay? And this is expected to be the Q-deformed Hamiltonian for fermions, okay? Okay, conclusion. For this case, I was attached to the space, the vector space of my superalgebra we consider the epsilon as a complex number, okay? For the Q-deformed oscillator, we can restore the non-deformed algebra very easily. It's the same, is approach very similar to the B andar. Doesn't change too much, but the fermionic case changes a lot, okay? So because of this, we need to verify the validity of this Q-deformed oscillator. So future perspectives, the first one is constructing the Q-bar deformed SU2 algebra, okay? Apply, I wrote applied, but is wrong. The right word is applying, sorry. apply in the Q-deformed statistical system, okay, and apply to this the cosmology to cosmology of Q-deformed dark matter and dark energy. In this article here, the author considered the energy, the dark energy, as a result of a Q-deformed spin-zero field. And the dark matter he considered as a Q-deformed field spin half, okay? So now let's go to the theta deformation in graded zeta 2 and superalgebra, okay? And in this algebra here, we want to create in quotes an algebra that has this definition for the Lie bracket, okay? The result must be commutation and a not commutation, okay? But firstly, I need to define, to present you this operator here that I call permutation operator, okay? I didn't find this operator in bibliography, so we had to create for this. And the definition of this operator is this here. He will act on this product, A, B. He will change, he will change permute the multiplication, okay, and add a phase that is exponential here. Okay, these are the important properties, the important operation properties operation for this operator T. Okay, and so in the beginning of my presentation, I said that the Lie bracket is a commutation or a not commutation, and the object that will define my Lie bracket as a commutation or a not commutation is the mapping. Okay, so I decided to introduce a small deformation in the definition of the mapping. Okay, so the mapping for a non-deformed algebra is 0, 1, but here I decide to add this term that in that epsilon is a deformation parameter, and theta is this operator here, defined in terms of the commutator, the permutation operator. Okay, so we did this change in the definition. Okay, and now let's calculate the result of this for epsilon very small. Okay, and for this we have when we are calculating, we do a small I said before, we do a small approximation for epsilon, and this exponential I consider only up to the first order of epsilon. Okay, and I have this result here. When epsilon is, when gamma is equal 0, I expected that my Lie bracket to be a commutation, only a commutation. But however, I introduce a perturbation. This result is a commutation and a not commutation, and vice versa. Okay. So I don't need to consider only very small values for epsilon. Okay, and I can get this general result here. Okay, so and here, of course. So a brief discussion about this result is these results are very similar to a Woloschenko algebra. Okay, very similar, but not the same. Similar result was, but with a different approach, was demonstrated by Mohapatra and by Greenberg. Okay, I intend to apply these results in system with broken symmetries, but more specifically in bosonization process and the phenomena of electron fractionalization. Okay, so that's all. That's the main bibliography of my presentation, and thank you for attention.
Thank you, Zach. In Q-deformity case, you expand in epsilon up to second order, right? No, yeah, yes.
I can write this expression here like this. Okay. And the second order of epsilon doesn't appear. Okay. I have 1, epsilon power 2, 3, and 5. And, okay, only all the powers. All the powers. Okay. So for example, let's in the place of this exponential here, let's put this expression. Okay, we calculate this, and NQ is equal N. Okay, we have to go up to the third order, or okay, why? I don't know. I don't know.
Isaac, before addressing a question about your Q deformation, I would like to ask you about the doubling that you just put some transparencies at the very beginning. So my question is the following. So you define some procedure to double the algebra on Z2 to Z2 to Z2 squared, Z2 cube, etc. And my question is that, so for instance, to make contact with Jeanne, she presented all algebra and superalgebra which are related with Z22. So do you know whether you can make classification and to say if all algebra, so which kind of algebra you can double from the previous one, and to see if it covers all space or let's say Z22 algebra, or there are some algebra that are genuine, existing in N equal 2 and cannot be obtained from double. Have you thought about this?
No, I don't know, but I think Mateus has, I think you proved, I don't know, or you try to prove this result, and I don't know which result he obtained. Okay.
We did just for a few examples, and we showed that if you do the doubling the way that he showed, you get a consistent Z2 graded algebra within the classification. But we did not calculate for every possibility to see if it covers all of the possibilities for zeta2, zeta2. So we don't know. Yeah.
Quite generous. So it would be interesting to understand if there are new algebras that are not obtained from doubling of previous algebra. So, or if the doubling exhausts all possibilities. That's quite interesting.
Just a comment that there are other type of doublings. Isaac showed with a minus sign on the odd sector, but you can double without the minus sign, and it will work too.
This minus signal was chosen in order to obtain these properties here. Okay. Okay, I wanted to keep well, I started from this algebra. He has a structure of a complex number, and I wanted to keep the relation of the doublet algebra with the division algebras. Okay, so this is how we can construct, for example, a quasi-non-associativity algebra, sorry.
Just a comment. If I remember well, there is a structure that is not that escapes the doubling. Yes, right? Just a comment.
What is I really don't understand what is Q bar and Q, why they're different. Can you return it, say 2 words about this? What is Q bar? You presented definition, and then you told Q is different. So
in Q the formula algebra, I think the only definition for Q is that. -1 and 1. In the case of fermionic and bosonic Q, the formula oscillators, the choice of a Q must be such that the representation should be unitary and irreducible. Okay, and so B. Andar told that he can be, for example, a complex number. Okay, my Q bar is a real number by definition. Okay. Sorry. The Q. I don't. Not necessarily. I think not necessarily. Okay.
Question.
My question is about the page 23. Sorry, a few pages before. One more. Yeah, this one. Sorry. Well, I'm not in this area, so maybe I'm I'm talking about a really silly question. So, to me, this relation in the left, yeah, this one. Remember me very much the temperature spectrum. I don't know. Certainly, it's don't have relation, but the epsilon could be interpreted in some way, like this deformation giving temperature to the electron, something like that. Electron of fermion.
Yes, I think yes, because well, maybe. Yeah. Here I wanted to I want to define a epsilon that is a kind of parameterization of, for example, physical perturbation in my system. Okay, but I think it's a good question. Sorry.
So can you see this number operator in Q deformation as somehow a Vita index in supersymmetry?
Isaac, I have a question because so first you told about a Bidenharn Q oscillator. There are several definitions of Q deform oscillator, and Bidenharn is one of them. So what you did is just a Bidenharn, or it's proposing another definition of a Q oscillator, and why this one? Which are the properties? Because in principle, one can make a lot of Q deformations.
No, what I did was the following. B and R, in the approach of B and R, we must choose the value for Q that this restriction here, the unitarity and the irreducibility of the representation must be valued. Okay, so if I choose a Q like my Q bar, this exponential here, we are respecting this condition. Okay, so I am working in the approach of B and R. It's not a new approach. Okay, I just using a possible value for Q that he didn't use it. Okay, and for the bosons, it works very similar to the results. Okay, but question here, it is not this observation when the exponential is expanded only up to the second order, and this expansion didn't express nothing of new on my system. This wasn't he didn't said nothing about that. Okay, but for fermions we had changes. Okay, but this restriction here is also must be respected for fermions. Okay, for the Q fermionic oscillator. So it's this.
More question or coffee? No? Coffee. Okay, thank you very much again. Thank you.
Okay, let us start the final session of this exciting meeting. So I'd like to invite Matheus Barbino from CBPF. He's telling us about tenfold way and associative superdivision algebras. So please.
Hello. Hi, everyone. Thank you for the opportunity to present my master degree work here. So, as I already mentioned, I'm a student here from Toppan, and on my master degree, I studied a lot superdivision algebras, mainly because of the paper by Toppan and Jana about the tenfold way and an extension of the tenfold way for zeta2 superdivision algebras. So I'm going to briefly talk first about Kelly-Dixon algebras, which is the main algebras that will enter the classification of superdivision algebras. And then I'm going to talk just a little bit about alphabetic representation. And later, I'm going to talk about the grading algebras, and the main part is here superdivision algebras. So here is only a bit of an introduction to show that we are applying all this type of algebras in physics from a lot of time right now. Clifford algebras, of course, and Kelly-Dixon algebras are the most famous. Everyone already knows Clifford algebras and Kelly-Dixon algebra, especially the associative ones. And our group are applying now graded algebras in physics. And me personally, I want to find a direct application for non-associative. For some reason, I really like octonions and split octonions, and I really want to find a direct application of non-associative in physics. So this has pushed me to study everything there is to know about non-associative algebras. So one of them, of course, are superdivision algebras. So it started with what we call the threefold way by Dyson, and the threefold way is formed by the threefold way is formed by the three division associative algebras, so the real numbers, the complex numbers, and the quaternions. So we use them in physics. So in quantum mechanics, we have a complex Hilbert space, but by show that we can, when we classificate the irreducible representations of groups on complex vector space, like the Hilbert space, it appears the three types of division algebras, the threefold way. So then the generalization to the super algebras came through with what we call the tenfold way. So now we have not only the three associative division algebras, but we can have a zeta2 grading of Kelly-Dixon algebras. And when we classify all of them, we get 10 total algebras, and this forms the tenfold way. And the tenfold way has already appeared in physics. So they are appearing in the classification of the topological insulators and superconductors. I put here the paper by Kitaev and Ryu et al. I'm going to show the reference in the last part. And there is a researcher here, Tobias, that works on this area. So we are planning to join with him to try to apply this on the topological insulators and superconductors. So just a brief introduction about the Kelly-Dixon algebras here. We are using mainly the Kelly-Dixon doubling construction, which is here, we can find here in this paper by Xavier. And there are just these 3 rules. So you get, you take a Cayley-Dickson algebra, let's say the real numbers, and you construct another algebra. Let's have an algebra that is double the dimension. That's what we call the doubling. And the doubling that you construct must obey this, the rule of multiplication, conjugation, and you have a norm. And this epsilon, it can be -1 or 1. When it is -1, you get a division algebra, and when it is +1, you get a split division algebra. That a split division algebra has this split type form, and the norm type of norm. It's not actually a norm, and this norm can be 0, can be negative, and everything. So, and of course, the split division algebras do not obey the property of being a division algebra, which is if you have a multiplication of 2 general elements going to 0, then A or B must be 0. In the split division algebra, this does not have to be true. So Cayley-Dickson algebra can be commutative, associative, and alternative. Here are the properties that the elements must obey. And the main ones, the more important ones here, the division algebra, the real, of course, are commutative, associative, and alternative. The complex too, they are also, but when we double from the complex to the quaternions and so on, you start losing the properties. So from the complex, when you double to the quaternions, you lose the property of commutativity. So the quaternions are anti-commutative. And when you go to the octonions, you lose the property of associativity. And when you go further for the octonions to what we call the sedenions, you lose the property of alternativity, and you lose the property of being a division algebra. From the sedenions and beyond, we don't have a division algebra. So even though I'm going to talk about sedenions and split sedenions, although they are both non-division algebras, but I am going to talk about sedenions that has an Euclidean norm, and split sedenions, which has that type of norm, a type of norm that can be positive, negative, or 0. So for all of them, to denote a split division, you just put a tilde above the field. So this is a work that was done primarily by Isaac. And Isaac found a general matrix representation or realization for all Cayley-Dickson algebras. And I went to defend my master's degree thesis, and Jaime Vaz mentioned to me that it already appeared in these 2 papers here. This book called Muffin Polygons by Titz et al., and a paper by Craig Kubert. So I checked these papers, and yet indeed they presented a 2x2 matrix realization for the octonions only, and a 2x2 with quaternionic entries in the matrix. Only that Isaac created the same matrix realization, the same one, but he did for all possible cases. He did for matrix realization for sedenions, split sedenions, octonions, split octonions, and not only 2x2, but 4x4, 8x8 for the sedenion, 16x16. So I put here his master's degree thesis by Isaac and mine, because I put a part of it on mine too. So what the matrix realization comes from checking a matrix representation for the complex, the split complex, and see and looking for a pattern. So you have the general matrix representation for the complex numbers, the split complex, and you go to the quaternions, and the matrices that we get are the same here. the X and Y are real, so the conjugate doesn't change the sign. So we can generalize it, and we see here that for the quaternions, X and Y are complex. So we can use this to create a doubling pattern. So for the octonions, X and Y will be quaternions. So we will get the 2 times 2 matrix realization for octonions. However, it is not explicitly, but just looking at this, the multiplication, the Katie-Dickson multiplication here, these matrices must obey this multiplication here from the doubling. When you put the Katie-Dickson doubling multiplication in a matrix form, in this matrix form here, you will see that the matrix multiplication for a matrix realization of a Katie-Dickson algebra must be the usual matrix representation plus a correction term that comes from the definition of the doubling. This correction term involves commutation of the elements of that goes into the matrix. So when we are up until the quaternions and split quaternions, you will have here a commutation of complex numbers, but complex numbers are commutative. So this term, correction term, goes to 0. So the complex split complex is the same thing. It's a real number, so it goes to 0. So for associative Katie-Dickson algebras, the matrix multiplication, if you have a matrix representation for the algebra, the matrix multiplication is the usual matrix multiplication. But when you go to a non-associative Katie-Dickson algebra, you must account for this correction term that can be non-zero. So that's the brilliance of this matrix realization that is constructed for every type of Katie-Dickson algebra, and you can also have the properties of conjugation and norm here. So this is only to show that we can grade the octonions, and we can use a matrix realization to grade the octonions that is compatible with the dimension of the algebra, because the octonions is an algebra with dimension 8. And we don't have a matrix realization for the octonions. We didn't have a matrix realization for the octonions that has a dimension 8. We had the Zorn matrices. Now, with this matrix representation here, or realization, with these properties, one can have an 8 times 8 real matrix realization for the octonions that has the same dimension of the algebra. So, and it obeys every property of the algebra. We already checked that. Yeah. I don't think so. I try to do like what you're saying. I forced the multiplication to be associative, but it did not generate the biquaternions. So I don't know what algebra it is. I didn't check the results again, but I don't think it will generate the biquaternions. Okay. I don't know. I have to check with Zach. I didn't do the calculations 2 times to check it, but I did not get the biquaternions. Okay. Yeah. Yeah, what Isaac is saying is that this matrices here was constructed by using the matrix, the doubling construction for the Cayley-Dickson algebras, but biquaternions it's basically a tensor product of the complex and the quaternion. So this is not the same type of matrix that we are talking about. So here I'm going to pass just right through. It's just the alphabetic representation. We are not going to use it so much. It's just the power that you gain when you take off the tensor product symbol, and you can present the matrices as words. And you can multiply them by using the properties of the tensor product. So when you multiply the two, for example, this here is a 4 times 4 real representation for the quaternions. When you multiply E1 with E2, you have to get E3, but you have the property of the tensor product that you can multiply the first element with the first element of the second vector that you are multiplying, and the second element of the first with the second. So you can use the alphabetic representation to do calculations pretty easily. But of course, this is just a topic, and I'm going to pass through here too. This is just the Cayley-Dickson doubling using the alphabetic representation. So these matrices here are 8 times 8 real matrices that represent, it's the matrix realization that I talked about for the octonions and split octonions. So these matrices here, they do not multiply only by usual matrix multiplication. You have to account for the correction term. And when you do that, the multiplication is closed, and every time that you multiply, for example, if you multiply E1 for E5, you get E6 and so on. So that's it. So now we can move on to the main topic, that is graded algebras. Everyone already talked about graded algebras. So I'm going to talk first about the graded Lie. So Rittenberg-Riley, I put here the fundamental papers, Rittenberg-Riley and Schoenert. And this one of Kuznetsov and Toppan is the classification that Jana showed us in her presentation. So a graded algebra, it's generally a graded space. So it's a vector space, and you can write it as a sum of subspaces. And we define the generalized commutator as using the bilinear mapping that which all the presentations are already mentioned. And by setting, of course, they are not free. We have ground rules for them. They are called the Leibniz rules. I think Jana showed the Leibniz rules. And here, either Leibniz rules. So you apply these properties here. These properties here are directly related with the graded Jacobi identity. So you have a graded algebra, and you define the graded commutator. And if you check that the elements of the graded algebra obeys this identity, you have a graded Lie superalgebra. This does not have to be true, as we will see in superdivision algebras. We do not care for that in the beginning. So we have zeta2. As we already mentioned, you have 2 gradings, so 2 spaces, the even and the odd sector, and you have only possible 2 bilinear mappings, 0 and alpha beta, possible that obeys these 3 relations here. So the first one gives the ordinary Lie algebra, and the second one will be the zeta2 graded superalgebra related to supersymmetry. But we can extend that, and this comes back to Jana and others' presentations of for zeta2, we have 4 subspaces, and you have 4 possible bilinear mappings. Rodrigo talked about the 4th, the Lie algebra, and Jana also. She mentioned about a graded Lie algebra for physical models. So it's the fourth bilinear mapping. And this gives us new types of particles called paraparticles. So here are the brackets table for them. Here is the table that Rodrigo showed in the beginning of our event. And the ones are anti-commutators, the zero are commutators. If you have an anti-commutator in the diagonal, you have a superalgebra. But okay, this is just a general matrix representation for zeta2, the even sector, the odd sector. This is a possible for zeta2, zeta2. There are more than one. This is only a choice. There are different types of convention for this. So now let's go into superdivision algebras. So superdivision algebras, it is a bit more simple. We are not, we do not concern in the beginning about the graded Jacobi identity. We are only talking about a graded vector space. Let's say, take an example for a zeta2. We have two subspaces, the even, the odd sector, and the only relations that we are the only relations that are important in the definition of superdivision algebras is the multiplication of the elements from this graded space. So the multiplication of elements from the even sector must give an element from the given sector. The multiplication of elements from the odd sector must give an element from the even sector, and the multiplication of an element from the even sector with an element of the odd sector must give an element of the odd sector. This happens too for Rittenberg-Riley, but on the superdivision, we start from this. This is the only important relations that we care. So now the main reference that I studied superdivision algebra is the reference by Bayes. It's called the 10th way. And Toppan and Jana did the generalization for zeta2, zeta2. They call the beyond 10th way 13 associative superdivision algebras. And by carefully reading the two papers, I saw that there was a difference in the beginning of the definition of the superdivision algebra. So let's suppose that E0 is an element from the even sector and E1 is an element from the odd sector. A homogeneous element for Bayes, for John Bayes, may be given by their sum, an element that it can be that has the both gradings. So grading is an even and an odd sector. That's what Bayes start with. Yeah, I checked the. Want to see? Okay. So and Toppan and Jana, they start defining superdivision algebra by stating that homogeneous elements are talking about homogeneous elements only within the graded sector. So if you have more than one element for the even sector, a homogeneous element for Toppan and Jana would be their sum, the linear combination of these elements. So this apparently would be lead to different results, but as I will show you, no, we will get the same results. It will be the same results. Bayes defines a superdivision algebra as a graded algebra in which every element from the algebra, including the homogeneous elements, are invertible, therefore forms a division algebra. And Toppan and Jana defines a superdivision algebra as a graded algebra in which every homogeneous elements from each individual sectors are invertible. Therefore, the graded sectors are isomorphic to one.
If we have superdivision algebra, divisionality is mais fraco, sim? Because only homogeneous elements should have in inverse. and mix should not to have. So not all elements. So it is understood. But if you have E1 plus E0 plus E1, it is not homogeneous element. In superdivision, you cannot require. But okay.
What I think Bayes does is that he starts from calling homogeneous elements the sum of the two graded sectors, but then he redefines, he rescales the odd element to get to a new superdivision algebra, where in this new superdivision algebra, the sum of elements from different graded sectors, they are not invertible. Okay. I can show you the. Okay. So Bayes, he says that you take an odd element, an element E from the odd sector, and because they are invertible, you can rescale this element. So, and a multiplication of these elements on the even sector makes that the two sectors, the even and the odd sector, are isomorphic. So if the even sector is isomorphic to the reals, the odd sector will also be isomorphic to the reals. So by taking this this element that Jana is mentioning that cannot be invertible, and saying that it is invertible, and saying that because we are talking about the even sector and the odd sector are real numbers, I am checking for a possible term to invert this as a linear combination. Oi? What? Okay. Okay, I understand. So
is that so you have an algebra. This algebra can have a Z2 graded structure. So you, as a vector space, is the sum of an even plus an odd sector. Maybe you can have different representation in introducing different type of splitting into even and odd. But the problem is that these different representations are absolutely equivalent. They're isomorphic because you can pass from one to another. So when you have defined your chosen grading, which generators belong to the even and which generators belong to the odd, then the fundamental property is that each of these sectors is invertible. So there is no contradiction. You understand?
yeah, sorry if I misunderstood the paper by Bayes, but I get what you're saying, and that's what I was showing, that after you do this rescaling of the odd elements, the new superdivision algebra with this rescaled odd element will not will not be invertible when you sum elements from different graded sectors. So I don't know if you understood. So I start considering that they are invertible, but then I solve this equation by considering you want a variable, and then this k term here, it can be equals to 1 or minus 1, and by rescaling this one with a new so I'm defining a new odd element E1 with a that is given by E0 plus V1, and the square of this new term will depend on k, because k will pass here, so will depend on the sign of k, and will be equal to 1 or minus 1. So after you will rescale the odd element, you will have the complex and the split complex for the zeta2 case. So by using E0 and now this rescaled E1 slash, I forgot how to say that, you will have the superdivision algebras when in the split division case, if you sum this E1, this rescaled E1 with E0, it will be a split division algebra, therefore the sum of the different graded sectors will not be invertible. Okay, so the two definitions lead to the same result. But as in the beginning of the introduction of Bayes, he mentions that homogeneous elements are some of different grading sectors. But when he does the analysis, he gets to a superdivision algebra where you cannot sum different elements from different graded sectors because they will not be invertible. Not generally, but in some cases they will not be invertible. So the classification of by Bayes is the same. Is the temporal way, of course, is the same than the Toppan, the method by Toppan. But Toppan and Jana started from graded sectors separately must be invertible. And Bayes, I think if you go to the introduction, quantum mechanics. No, I think it's the temporal way. The temporal way. Okay. But I know that this is strange. We can check the paper together, but the important thing is that in the last after doing the analysis, the superdivision algebra are the same, and the conclusion are the same. And a superdivision algebra is an algebra where homogeneous elements within the graded sectors from each graded sector separately must be invertible, not necessarily this homogeneous elements from different graded sectors. Okay, that's the important thing. So okay, we can grade Cayley-Dickson algebras. If the homogeneous generates that compose each sector, each grading sector are invertible, then we can call it, I will call it a SDA to not call every time superdivision algebra. And the multiplication rules, of course, must remain valid. And the split division algebras, which are not division algebras, and the Sedenions and beyond that are also not a division algebra, can generate as SDAs. So when you grade them, you separate the elements within the graded sectors. And when you do that, you take off this the property of being a split division algebra, because you cannot now sum elements from this from different gradings. So you can use the split division algebras to generate super division algebras. Superdivision algebras can be associative and non-associative. Of course, there are octonials. Octonials are division algebras. So when we go to the super algebra case, of course, we need to have non-associative superdivision algebras too. And the inequivalent SDAs will be given by the graded subalgebras that they have, which I will show. So the classification done by Bice on the paper tenfold way is the following. Here are the 10. So we have the free division algebras, associative division algebras, and they are all in the even sector, and the odd sector has no element. And then we go to the super algebras, to the zeta 2 case. So he starts by for the real case. So the even and odd sectors are isomorphic to the reals, and we have an odd element in the odd sector with a square equals to 1, and the other type of superalgebra we will have an odd element with a square equals to -1. And when the graded sectors are isomorphic to the complex, we have 3 superdivision algebras, one with an odd element from the odd sector that commutes with the imaginary number and has the square equals 1, and other 2 for anti-commutation with the imaginary number equals 1 and the square equals 1 or -1. And last 2 for quaternionic case, and the graded sectors are morphed to the quaternions, and an odd element E that commutes with everything in the even sector and has a square equals 1 or -1. So these are the superdivision algebras for the tenfold way. And these are the algebras that are being applied in the Kitaev periodic table of topological insulators. And here is from my thesis. So I did in a bit different way that by Bice, I used the tensor product between Caylor-Dickson algebras. And I'm just going to show you that they are the same superdivision algebras. So the first 2, the real ones, it's easy to see that these first 2 here, the 4th and the 5th, are the split complex, the 4th, and the 5th are the complex numbers. That is what I'm saying here. The first one, a zeta 2 gradient of the complex, and the zeta 2 gradient of the split complex. The 3 quaternionic complex ones. So we have a zeta 2 gradient of the quaternions, split quaternions, and the B complex. So the quaternions have 4 elements, 4 vectors, and you separate in the middle. So E0 and E1 goes to the even sector, E2 and E3 goes to the odd sector. And if you take, for example, on the quaternions, E2, it's a vector that its square equals -1, and E2 anti-commutes with E1, and E1 is in the even sector. So we get here the superdivision algebra 8 from Bice. Okay, so for the split quaternions, it's the square equals 1 because of the split metric. So we get the other type, and the last one is the B complex, whether there is an element that goes into the odd sector, which I called here E3, but it's the tensor product of the imaginary with itself 2 times, and the square goes to 1, and it commutes with all the elements in the even sector. So we get here superdivision algebra 6 by Bice, okay? And the quaternionic ones, the same thing. So we have the biquaternions and the split biquaternions, and basically a tensor product of the complex with the quaternions and the split complex with the quaternions. And in this case here, you can take the element that you do the tensor product of the imaginary with the scalar of the identity of the quaternions, this element here, the square of it is -1, and it commutes with all of the elements that goes into the even sector that are the quaternions, of course. And from the split quaternion is the same, but the square of it would be equals to 1. So we found out all of the tenfold way. We get the tenfold way here. So here is the tenfold way in two ways to see the tenfold way. And here I'm going to present that something new, that I put in my thesis, but not in this way. I'm presenting like the way that Bice presents, the non-associative case. So we have another division algebra that is a non-associative. There are the octonions. So we have here the octonions, a superdivision algebra with the trivial grading. All the elements goes into the even sector and none of it goes to the odd sector. But we can have, of course, the zeta2 grading of the octonions. We have two quaternionic types. What do I mean by quaternionic? Well, the octonions, all Cayley-Dickson algebras have a property of having S sub algebra, another less dimension Cayley-Dickson algebra. So the octonions and the split octonions, they have S sub algebra, the quaternions. So we can have a non-associative superdivision algebra where each grading is formed by a quaternionic type of a quaternionic algebra. So we separate the octonions and the split octonions in half. The first four elements are the quaternions, and the last four are what we call the non-associative bases. They can be isomorphic to the quaternions. And with the octonions, all the elements, the square equals to -1, and with the split octonions, you have in the odd sector elements that square equals 1. But of course, we can have non-associative superdivision algebras where the graded sectors are the octonions, the octonionic field. So this will be, there will be 4 cases, and one case where you can find an odd element E that commutes with everything in the even sector and has the square equals -1, and another case where the square equals 1. And the other two, you find a element E, a square equals -1 and square equals 1. In this case here, there is no specific commutation or anti-commutation. This odd element anti-commutes with most of the elements of the even sector, but it commutes also with the identity of the even sector. Yes. Okay, yes. Yes, yeah. Yes, I have to, I don't know, I have to, we have to find a way to write this better, but it should come with an asterisk to point out that the total graded algebra, the total algebra is non-associative. No. So here it will be more clear. It's in the way of tensor product. So the first two, of course, is a zeta2 grading of the octonions and split octonions. This the one that Toppan mentioned and not right now. And the fourth from the other fourth cases are the bioctonions, the split bioctonions, the sedenions, and the split sedenions. So on the bioctonions, you have the tensor product of the imaginary with the identity of the octonions. This element, the square of it is equal to -1, and it will commute with every element of the octonionic basic that will be the V sector. So, so this goes here. So this case here, the case 4. And the split bioctonions is the same, but now it will be the split imaginary, so it will square to 1. And the sedenions, of course, all elements in the V sector is squared to -1, and the split sedenions, all elements of the odd sector is squared to 1. So it have the last 2 cases. So this would be a classification that is not done. There is no paper that has done this classification. So this needs to be further studied. And this is just to point out that there are, of course, the paper by Kuznetsov and Toppan that classificates the associative superdivision algebras, and now you have 4 gradings. So when you go to the real case of now, we are not talking about complex and split complex, but algebras with dimension 4. So we have more cases, and we can check the paper by Kuznetsov and Toppan to see the complete classification. And in my master's degree, I also did the non-associative case for the zeta 2 case, but I'm not going to show because it's going to be too big. So to finish, I talked about that in superdivision algebras, we are not worried in the beginning with the definition of a commutator or anti-commutator with the bilinear mapping from Rittenberg-Riley and the table of brackets, the graded Jacobi identity. But of course, we can check if they obey. Of course, for non-associative algebras, we already know that the octonions and split octonions do not obey the Jacobi identity. They obey a more general algebra that we call the first study by Malsev. I put here the paper by Malsev and here the paper by Sigaud about Malsev algebras. So we defined a product that is a commutator, so the square equals 0, and here every product here is a commutator. Okay, so this is the generalization of the Jacobi identity. This is the Malsev identity, and we can put this identity in this way here. It's the same thing. It will generate this. So this J, X, Y, Zeta is the Jacobi identity. So normally in a graded Lie algebra, in a Lie algebra, this Jacobian goes to 0. So, but in the Malsev algebra now, so we can use the Jacobi identity to create the Malsev. So every associative algebra obeys the Malsev algebra, but an octonion do not obey the Jacobi identity, only the Malsev identity. Okay. So the Sigaud identity are similar to the, it also generates a Malsev algebra, only for fields of characteristic different than 2, you can use the Sigaud identity. So, and the split octonions are also a Malsev algebra. So here I put reference on graded Malsev superalgebras. They already started being defined. I think it started in 1993. And Shestakov, Albuquerque were the first ones that I saw writing about graded Malsev superalgebras. And how do you do that? The same way that we did for graded Lie. For Lie algebras, we generated graded Lie. Now we talk about the commutator. So this is the same of the graded Lie. We will have the abilinear mapping, but we have to grade the Malsev identity. And the way to do that is to use this formula for the Malsev identity. And what we do is we change the Jacobian to the graded Jacobi identity. So now this J bar is the graded Jacobi identity, not the Jacobi identity. And when we do that, we are talking about a graded Malsev superalgebra. So this I took from the papers Shestakov and Albuquerque. This is a graded Sigaud identity. So this is already been defined in the literature. And if we want to talk about non-associative superdivision algebras, we must see if they obey. Of course, I think they will obey this relation. But be careful. This is for octonions and split octonions, because sedenions and beyond do not obey a Malsev algebra. So we are talking explicitly about octonions and split octonions here. So, and this is a note. We talked about grading Cayley-Dickson algebras. We talked about the trivial grading, what we call the trivial grading. That is, we put the field, all of the field in the even sector and none in the odd sector. And we talked about a non-trivial grading that we separate the field in half. So elements goes into the even sector and the odd sector in a split way. But we can have other types of grading. So we can have a different type of grading, and let's separate the identity of the Cayley-Dickson algebra. I would denote it here with K0. I know that it's not good, but just to point out that we are talking only about the identity of the algebra, and I put the vector part as a with a vector above it. So there is also a non-trivial grading. I think Rodin and Jaime call it the usual grading. And this grading, you put the identity in the even sector and all of the vectors of the Cayley-Dickson algebra in the odd sector. So now we are not talking about a graded superdivision algebra, because one of the properties of the superdivision algebra that we mentioned is that the graded sectors must be isomorphic. So when we do that, we are only talking about a non-associative graded Malsev superalgebra in the case of split octonions and octonions, or a general non-associative graded superalgebra. So we have to be careful. We have to more than one way. And there are, of course, we cannot grade we cannot grade the way we want, of course. It has to obey the multiplication rules. So we have to be careful. So this is it, I think, to conclude. So superdivision algebras can be used to find zeta to the power n grade superalgebras for physics applications, that the work that we are showing in this event. And they are appearing in the periodic table of topological insulates and superconductors. This is the main purpose to study non-associative superdivision algebras, to see if we can find a non-associative superdivision algebra in a classification of topological insulators. And that's why we want to collaborate with Tobias to help study this. And on my master degree, I studied this classification to leave a clear base reference for the future. So I was not worried in the beginning for physical models. So we started by only classifying and studying the superdivision algebras, so that we know the complete set of what we are dealing with to apply in physics. And I really think that non-associative can find its direct way into physics. So I really want to pursue this, but this is something to be done, of course. So there's nothing pretty concrete on this yet, of course. So here's the paper that I mentioned to Jana. This is the paper, the 10th way, Notes of the American Mathematical Society. Here is where Bayes defines the superdivision algebras, and we can check the way that he wrote. So I put here the papers of quadratic Moussev superalgebras and papers, of course, on the octonions. This is the most famous paper on octonions, and so on. This is my master degree thesis, and this is the paper that I mentioned about the exact matrices that by Craig Kubert, and here is Isaac's master degree thesis, where he does the complete analysis. And I put here some of the papers where we apply, Jana and Toppan apply. Here is the paper beyond the 10th way, the 13 associative. We call it 13 because now we have zeta 2, so we have more possibilities of superdivision algebras. So when we count the total real complex and quaternionic, we get a 13, of course, but it's beyond the 10th way, of course. So that's it. I have some other papers here, but if you want, I can show later. Okay, so that's it. Thank you. Thank you, everyone.
Okay, thank you for the talk. Any questions?
Matheus, you said that we can grade, I think it's on page 20. Okay, yeah. You said that we can grade the Cayley-Dickson algebra. And so do you know what kind of, yes, for example, octonions are a Moussev algebra, graded, for example, a graded Moussev algebra. And which kind of algebra are Sedenions? Graded algebra are Sedenions, don't you know? Okay. So I'm thinking that is not a question on for you, but for everyone. Is the following. Can I say that the Lie algebras are a specific kind of Moussev algebra? For example, okay, so yes, that's all. I think because I'm thinking about generalizing like, for example, in Cayley-Dickson, we can go for from a associative algebra for a non-associative, and if we continue, we go for a non-alternative. So I think that if there exists a method of transforming the graded algebras, okay, or if there is a general algebra with all these properties, the non-alternativity, okay? So.
I think it's a nice. I think it's a nice question. I don't know. I didn't check, but I think that it could be a possibility to take a graded Lie and try to find a graded Moussev. I don't know, but of course, if a graded Lie superalgebra, I think I didn't check. It must obey the graded Moussev identity. I think. Okay.
No, that's important to work on non-associative superdivision algebra. That's because no one has done it, in fact. Concerning the question about that Isaac, I don't know, in fact, if people tried to generalize the notion of, because the Sedenions are non-alternative, and Moussev algebra is a very well-defined mathematical structure. So I don't have idea what is done beyond that. Concerning the comment, Mateus, this is exactly the same. You see, the point is the following. Bayes said how to construct a
this is paper by Bayes, which you mentioned. And Bayes says, here I... Yes. Superdivision algebra is superalgebra such that every non-zero homogeneous element has its inverse. And this is a paper which the tenfold way. So, and you told that not every, and Bayes says that every. So means that we have the same approach.
No,
No?
sorry.
But maybe you mean different things.
He says, I said that they are non-invertible. That has inverse. Yes, okay. So I wanted to say that both of you said that the homogeneous element has inverse. But the way that Bayes defined here in above is that homogeneous is if it is either even or odd. Yes, it is even or odd. So the way that I understood this is that the homogeneous element for him could be a linear combination of V0 and V1 in the beginning. And then when he goes to the analysis, he says that the graded sectors are isomorphic. And so if you take an element E, I'm not seeing here, and where is so he does this analysis, and since he says that the graded vector space are isomorphic, and when the E0 is the reals, we can rescale E the way that I think it's the way that I show to obtain either square equals 1 or square equals -1. And when you do that, you get to the superdivision algebra where you cannot sum the different graded sectors, you know. So my comment was about this definition here of what is a homogeneous element. He says we say an element of V is even if it lies in V0, odd if it lies in V1, and homogeneous if it is either even or odd. The way I understood is that we can combine the two, you know.
I see that. Yeah. Because here you should either, it is some strange word, or it is important word here. So either even or odd. Can I make, I'm sorry, one more comment about Isaac's question. So we have Maltsev, he defined, for example, associator, a combination of 3 elements in product is equal 0. This associative. Maltsev defined combination of 4 element products, yes? And it is, in principle, can appear question, you have 5 elements, 6 elements, but maybe it is redundant to 3 elements. Who knows? We don't know. I don't know.
So this part here. So I think it was a misunderstanding for my part of the way that Bayes said. So yeah. So all of this here. So I think it can be disconsidered. I think. Okay.
Now, look, the point is the following. I give you here the example. So you have, let's say you have quaternions, right? And before introducing any grading, any Z2 grading, okay, they're just quaternions. Now you have to introduce a Z2 grading. And it means that you have to put some even sector and some odd sector. And you have equivalent choice to do that. For instance, in this choice here, you have, of course, the identity plus some imaginary quaternions, one of them, and you associate the event setter in this way. But you can have another choice of another element, which is this, and you can associate the event setter in this way, and the other are odd, and you realize a superdivision algebra based on this. But once you have done these are completely equivalent because they are isomorphic. So the point is, once you have one of these element with the square is +1 or -1, that's enough. You know that in this algebra it is this. So there are isomorphic.
Thank you, Toppan.
Any other comment or questions? No? Okay, let's thank the speaker again. Okay, now I'd like to invite our final speaker, Professor Toppan from CBPF. Yeah. Go. So the final speaker, Professor Toppan, we should wait for a while. Actually, I not so read that I tried to read it, but I didn't understand it. I think it was not too specific.
When you write people who write poetry like to be ambiguous, to have different types of interpretations. But when in a mathematical paper, this is something that one should try to avoid. The most important part of the talk is to understand but this point non associative very high. And this should be
You know, mathematicians are a machine. If you give a code to mathematicians, they produce a COTEO. It means the one we discussed on mathematics has always been solved. If you make coefficient, you can get some COTEO. Yeah. Okay, let us start the final talk. I'd like to invite Professor Toppan. Okay, he's talking about statistical transmutation of superconformal quantum mechanics and their spectrum generating algebra. Please.
Thank you, Naru. Thanks. Thank everybody. Okay, I will stay here. Okay, everybody's very tired. We had a very long day, so I will try to be not to be so boring. Let's say. Okay, so this is my talk, and the talk is made in 3 parts: part 0, part 1, and part 2. And part 1 is based on this paper that was put on archive 1 week ago, together with the very brilliant student Mateus, Rodrigo, and Isaac. Okay, I can skip a lot of things because I already, especially Rodrigo, that presented, also Jana and Mateus, part of the construction, and Isaac as well. So part 0 is the introductory remarks, but you have already seen this kind of transparency in the morning, so I can skip about all these people that work on this kind of subject, which in a sense had a boost in the recent years. And now, so that's one point of the focus which I want to mention, because you see, when this system appeared, and especially when the model by Bruce and Dupli on quantum mechanics appeared, then there was a question, because they presented a model, a quantum model, which has a Z to Z2 graded superalgebra, super Poincaré, but this is also a model of supersymmetric quantum mechanics. So, okay, and then of course there is a question about what happens with this kind of structure, right? Because sorry, the Z2 is just a cherry on a cake, but people want also to have a cake. So there was a question, very serious question, and then when we continue to produce this kind of work, because we found all this theory very relevant. The question remained even with the referees. We had a very strange report by referees in some journal that we were even somehow pleased to have this, because it means that you are in a right track. But there was a question: what is the physical relevance of this model? And that's the point. So, and for this reason, one has to find out a way to justify in the foundation that these systems are really relevant, because they can give some inequivalent consequences which is not obtained from other systems in some very selected examples. So that is that was already mentioned by Rodrigo, by the way. And I want to tell a story, okay? And the story is about, because this started, in fact, all this activity of Z2 started when we visited for the first time Professor Aizawa in Osaka. It was in 2015, and we started questioning how can we find the Z2 application, graded application. So at the end, we ended up that they appear in symmetry of non-relativistic Lévy-Leblond spinors. And we were exposed to these very brilliant no theater piece, Lady Aoi Noe. And you know, no theater is very ritualized and very minimalistic. So this piece is about the minimalism comes from this. There is the character who gave name of this piece, Lady Aoi, she's the main character, but she does not appear on the stage. She's ill. There is a projection of vengeful spirit of Lady Rokujo that hit her. So she's ill all the time. And Lady Aoi is never on the stage. She's represented here by, oops, did it go back? What happened? By this. This is a vest, a cosode. It's a kind of vest. He's laid on the ground and represent her. Just it. Everything is very minimalistic. And why I take this? Because this is something which is very much in my spirit, because sometimes, and this I want to tell to the students, instead of complicating things, you have to go to very simplified matter as much as possible to find out in which minimal setting some ideas can be tested. And was pleased today that the talk by Maurizio that also had some similar minimalistic approach, because he had a very very problem to solve in general relativity concerning the gauging of general relativity, and so he decided to go to a very special setting to consider wordline method. So that's exactly what I'm telling about the reason. So, okay, this I can skip because this was already in Rodrigo. But what I want to say is that, you know, we have these, this is not contained, by the way, in the Rittenberg-Wheeler paper, but if you take a Z2N graded associative ring of operator, the number of graded algebra which satisfy graded Jacobi identity, which are induced by that, is given by this number here, which contain the floor function. So for n equal 2, you have 4, for n equal 5, you have 2, n equal 3, you have 5, for n equal 4, you have 7, and so on and so on. And the point is that you have to treat all of them democratically. So you don't select just one, you want to analyze all possible consequences of this, okay? And this represents a model-independent lower bound on the possible inequivalent graded Lie superalgebra that are induced. Why? Because the operators, you see, that we have, initially, they can all on equal footing, like for instance, for the imaginary quaternions, you don't distinguish the 3 imaginary quaternions. You can, they're absolutely equivalent. But if you take a split quaternions, you know that one of them, the squared, is different from the other 2. So there are some extra possibility. This extra operator is marked. And so we have this kind of extra condition, which are Cn are model dependent. And here are some kind of computation that appear in our paper. Now, this is something I like, because this is a Fano plane. I love the Fano plane. It's a very beautiful structure. And this is how it is related with Z23. So we already seen grading. Jana presented, and not only Jana, the 4x4 matrices with the Z2, Z2 grading. Here I go to the further case, the Z23 grading. So it is given by 8x8 matrices. And here you see, you have this 8 sector. Of course, the diagonal is always the 0 sector. And then you have the non-zero sector, which are outside the diagonal. Okay? Now, take these 2 matrices, for instance, alpha and beta. Whatever are the entries in alpha and beta, you multiply and you get something which is this type of matrices whose grading is alpha plus beta. And now the beauty things is the following, that when you do that, you have one of the implementation of the Fano plane. The Fano plane is mostly known because it encodes the non-associativity of the octonions, but here it is in a completely associative framework, multiplying how you multiply this grading of associative matrices. Okay, so this is one very nice implementation of the Fano plane. I'll see how this will be relevant later on. Okay, this is the classes of equivalence of the grading sector. I mentioned that okay, just to give you some example explicitly, I take one of the 5 tables of Z23 grading. There are 5, and this is one of them. This is the 4th case. You can see that this is a Z23 graded superalgebra, color superalgebra. Why? Because there are 2 elements here. Sorry, I need to go a little bit here. Are type of parafermions here, because you see in the diagonal and also this one. So there are not only bosons or parabosons, which are 0, so they anti-commute, so they satisfy the Pauli exclusion principle. But here you can also see something else. You can see from here that there are one line where you have only 0. This is the 0 sector. It is obvious that there are only 0. This is assessed by definition. But here there is an extra sector which is non-vanishing, which is only 0, which means it is a boson. And the other sector here are of parabosonic type because they are not fermions or parafermions, but sometimes anti-commute with other generator. Well, this one is a real boson. Okay, so there are several possibilities. Okay, now the question of the detectability of n-bit parastatistics was already mentioned today by Rodrigo, and I give you another construction right now, which is even more interesting. So, okay, I can skip also. This is how we use the coproduct by using the approach of Majid concerning the Brady tensor product. I can skip it because Rodrigo already introduced this. Thanks, Rodrigo. But then I go to something which is really, I was surprised when I saw this result, because I have a better way to detect parastatistics than in the previous system. In this kind of example, the parastatistics can be detected by looking at the spectrum of the degeneracy of the energy level. And this was not noticed before, not realized before. So now I'm talking about the statistical transmutation of the supersymmetric quantum mechanics. Okay, Professor Aizawa already mentioned n=2 supersymmetric quantum mechanics. When you have a Hamiltonian, you have 2 supercharges which anti-commute, and the Hamiltonian commute with the charges, with the supercharges, but you can extend to n of them. These values, 1, 2, 4, 8, are the most investigated in the literature because they are simpler and because they are related with division algebra. And n=8 is the most interesting because it's related with octonion, right? So, okay, I can skip this technical part, but what I want to say is that in the minimal representation in terms of differential operator, if you have an n=1 supersymmetry, you have to realize it in terms of 2 times 2 matrices. If you have an n=2, the matrix should be 4 times 4. For n=4, they're 8 times 8, and for n=8, they're 16 times 16. And if you do that, it means that you can introduce a 1-bit grading, Z2, for n=1, a Z2 structure for the n=2 supersymmetry, a Z23 structure 3-bit for n equal 4, and a 4-bit Z2-4 structure for n equal 8 supersymmetry. That is the idea. And this is the fascinating point about n equal 8. I give you the most complicated example. In n equal 8, you should accommodate this object into matrices which are 16 times 16. Then what happens? It happens the following. You have 8 supercharges that you have to accommodate into the 15 available places beside the identity. So the supercharges should have non-zero grading, 4-bit for n equal 8. And then there are some fascinating points that happens, because it means that you accommodate some 8 of the supercharges in these 15, and then you left empty the other 7 sector. Okay. And then we have these, in some interesting cases, like these cases here, you have a tail of 2 Fanos plane. I give you an example. Let's take one of the graded brackets of 4-bit. There are 7. This is the case number 6. Okay? It is quite complicated. There are all commutator and anti-commutator that are encoded here. And now you can see the following here, that if you count on the diagonal, what you have here, you have on the diagonal, there are 8 fields, 8 generators that are fermions or parafermions, and the other 7 are bosons or parabosons. And now what happens? It happens something fascinating. You know, when you take 2 bosons and you make 2 bosons together, what you get? You get another boson. If you take a boson as a fermions, you get a fermions. If you take 2 fermions, you get a boson, right? With bosons and parabosons happens the same thing. So bosons and parabosons, they are absolutely close the algebra structure. And since there are 7 of them, what happens is that you realize the 7 of them close the Fano plane that I showed you before. This is for bosons and parabosons of this table. And you can prove that. You can show that. But remember that you don't have only bosons and parabosons. Now you have to decide if you have some supersymmetry generator, there are 8, to which of these slots to put. You have 8 and you have 7 of them which are empty. And the 7 empty you can represent like vanishing matrices. But when you have vanishing matrices, a vanishing matrix which multiply another vanishing matrix, there are 7 of them, they also close another Fano plane, and you have another Fano plane here, which goes this way. Okay? So this is for bosons, paraboson, and this is for the empty slot, this way. So at the end, you have 2 Fano plane. And what I want to do, let me put one Fano plane on my left hand, another Fano plane on the right hand. So the rule are that in this merging, you have only 2 possibilities. The merging can, all the 7 can fit all the Fano plane of the bosons and parabosons, like here, or they should be on the line. But look at here. In this case, you have some parabosons, but you also have, you can see from here, just a moment, a purely bosonic particle, which means that this is marked. Okay, so I say bosonic particle is here, and this means that here there is one generator in this boson paraboson Fano plane, which is marked. So this means that you have here 3 different cases. Okay? And this is for one of the 7 contributions. So now you analyze all the n equal 8 and you get this kind of table. And I represent this kind of table with all possible assignment of boson, paraboson, fermions, parafermions for the 8 supercharges. They're all inequivalent. Okay? And we have 14 different cases. So this is the for n equal 2, you have 6 cases. For n equal 4, you have 10. For n equal 8, you have 14, and so. And we should treat them all democratically. That's it. Now, detecting statistical transmutation, and that is the point. How we can do now to see if these things are detectable or not. I take the simplest example. The simplest example is something that everybody here is familiar because we worked with Maurizio some superconformal quantum mechanics, with the Alfaro-Fubini-Furlan generator. We work with Isaba. So this is the n equal 2 superconformal algebra realized by this kind of matrices with the 2 supercharges. So this is n equal 2, the conformal partner. And then you can see here that we have add this term here, the oscillator term. You have a Hamiltonian of type the Alfaro-Fubini-Furlan, and the supercharging the conformal partner, you can combine to create 2 pairs of creation annihilation operator, and this creation annihilation operator, they satisfy some operation. Their anticommutator is this one. If you take their commutator, you have a type of deformed Heisenberg algebra where a Klein operator appears, like the one that many of you are familiar. It's okay. This is the setting. Now, the idea is the following. Let us take this kind of theory and let us perform all possible analysis on the 6 case when we statistically transmuted this generator, requiring that they are not only fermionic, but can be boson, parabosons, fermions, paraboson, etc. So, and then we have this relation for 2 particle case, which contains the coproduct, and you see the coproduct has this kind of sign appear here. And this kind of sign which appear here are related with the possible choices of parastatistics. There are 3 independent signs. They have 8 choices, and these 8 choices correspond to 6 possible type of parastatistic. One of them is the original fermion-fermion statistics. Okay, and the other are boson-boson, fermion-boson, etc. And since you have this, this sign here, okay, some of these states can collapse to be the same. For instance, if delta 1, 1 is equal to delta 2, 2, or if delta 1, 2 is equal minus. So these are the conditions. And then you can analyze, as Rodrigo did in the morning, the degeneracy of the energy level. So this is the vacuum energy, this is the first excited state, and this is the second excited state. But contrary to the example that Rodrigo mentioned in the morning, here it happens the following. The energy level are all the same, but what happens? In the standard supersymmetry, n equal 2, the tower of state is always protected to be 2. 2, 2, 2, this is condition of supersymmetry. But if we perform a change of statistic, transmutation of statistic of this operator, we declare there are 2 bosons, or 1 boson and 1 fermion, you have this number of states, there are 4. And we have 3 Z2 parastatistics, where we have parabosons or parafermions. And you see this number here is different. We cannot discriminate what are radar, the three of them, but we can say that if we have this kind of spectrum, necessarily we are obliged to introduce one of the three parastatistics, genuine parastatistics Z2, Z2, which are not bosons, ordinary bosons and fermions, coming from this analysis. And this is new, because in all the other examples, we have to introduce other observable beyond the Hamiltonian, beyond the energy, to make this kind of analysis. This is new. And of course, this is the conclusions of that Professor Aizaba already told about these Cuerda, Alderete, and collaborator achievements concerning simulating and producing the laboratory, engineering laboratory, different type of parastatistics. But now I want to give something about the spectrum generating statistical transmitted algebra. So you have some time. This is given in the following way, because I didn't have time to put on LaTeX. Okay, this is something brand new. You see, here you have what you have. You have the originally creation operator, which are fermionic. You have this kind of algebra. You take the coproduct, and since the coproduct preserve the algebraic structure, the same relations are preserved in the two particle sector. But now, what happens if I take the same operator and I switch them? I declare there are bosons. I can do that, right? And then I analyze the consequences of that. So here are the 6 cases corresponding to the 6 possibilities that are induced by the two-graded algebra. They can be 2 fermions, 1 boson, 1 fermion, 2 bosons, or the genuine Z2 parastatistic with the parabosons and parafermions. Okay? And now let us do what happens if they are bosons. This looks quite complicated because you see, P and Q anti-commute. But if you take the commutator, because now I have to take the commutator, they produce something new, which I call W. And now I want to check the algebra of all these operators, and the algebra of P and W and Q and W produce some nonlinear relation that you can see here. If I take the coproduct in the two-particle sector, I put with the bar, I have this kind of a relation here. And you can see that some of the parameters here are fixed, which tells you that the coproduct preserve this kind of algebra, nonlinear algebra, with this kind of relation. Okay. And this is the simplest presentation of this boson-boson nonlinear algebra, which we can use as a spectrum generating algebra to derive the degeneracy of the energy level. If I take fermion and boson, I have a similar kind of structure, and you can see that I'm obliged to introduce a Z. Why Z? Because Z is the anticommutator of P and P, but the BQ is a boson, so there is no such kind of anticommutator for Q because it's a boson. The commutator of P and Q again produce a W, but W anticommutator, this is a fermionic now, anticommutator give a central charge, and then you have some relation which is again nonlinear here. Okay? And that is a fascinating example. Now, take this P and Q and declare there to be parabosons. But what does it mean to be paraboson? It means the following. Oops. If P is a paraboson and Q is a paraboson, I don't take any anticommutator, right? Because they don't take as anticommutator because they're bosonic. But if they're parabosons, it means that you put them in one sector, you put the other in the other sector, and then you have to take the anticommutator, right? But we know what is the anticommutator of these guys are. Because the originally are the two fermionic supercharges. So the anticommutator is just 0. And that's it. How simple is this algebra, right? Comparing with the bosonic case, which is a nonlinear algebra, which require introduction to this. Okay. Then you can do for parabosons and parafermions. So this is a complete algebra, also very simple. And for parafermio and parafermions is slightly more complicated, but it's also very simple. And now let's do the analysis of how to derive the spectrum. Okay, I don't do for, okay, I have done for all of them, but I can show you the derivation for boson-boson. Remember, boson-boson, we have a very complicated nonlinear algebra, given by relations like this one, which are preserving to particle level. But this tells you, for instance, what this relation tells that, if you have a Q bar, P bar, you can always put the Q bar on the right side of P bar, and W bar survive. And then from this relation, you said that W P bar, you can always put the W bar on the right side of P bar. And then so you got at the end, like we have a non-commutative element, you can choose a ordering, like Dick ordering, while ordering. In this case, the chosen ordering is this one. You can put all the P on the right, all the Q all the P on the left, all the Q on the right, and in the middle you have the W. But since W squared you can represent with just a combination of elements which are 1W or not, at the end you have this kind of structure where this exponent in the middle can be just 0 and 1. So if you do that, you can construct the tower of independent state, which gives this number of this state here, and you can go on further and further, and it is absolutely obvious what they are. They algorithmically, and then you get this. And this is the degeneracy of the level in the case for all type of energy level. We start L equals 0, represent the vacuum energy, L equal 1, the first excited state, the second excited state, etc. You perform this analysis, and for this case, BB and BF, you have this number, so the degeneracy grows like 2L. In the original fermionic case, it is obvious that you have only 2. It meant because this is what is preserved by supersymmetry. This is what it tells. But what happened for paraboson, parafermions? You have this kind of, they grow linearly in this way. And it is also very easy to understand that because for parabosons, go back here, you see, for these guys of parabosons, this create one energy level. This creates one energy level. So at the end, here you have just the identity at L equals 0. At L equal 1, you can have P or Q. At L equal 2, you can have only what? P squared, PQ, and Q squared. So there are just 3. At L equal 3, you get P cube, P squared Q, PQ squared, and Q cube. And there are 4. And you can prove that they're all independent. You can even check putting Mathematica that is work this way and so on. And you see that this kind of analysis tells you that they grow in this way. And these numbers are different from this number. So this means that if you want to reproduce this kind of spectrum for this model, you need to introduce the two credit statistics. Which one of the 3? You don't know. For the moment, this reproduce for this kind of analysis the same result. What happened in more complicated case like n equals 4, when you have D21 alpha? What happened when you introduce some operator which are related with R symmetry? That's another question that I will not show you here because I don't have any answer, but that is the point. And I think I can finish my talk here.
All these choices for the grading contain the same information, or you lose information like constant of structures or something?
You see, I give you two operator that are ladder operator for originally for superconformal quantum mechanics. Okay, there are two ladder operator. Now I can declare, of course, that this operator, given the have operator, I can associate a different type of statistics and parastatistics. I can analyze the consequences of this. There are 6 possibilities that I show there coming from our analysis. And these consequences tells you in this particular case, by using just these, okay, it is here, just this kind of simple analysis. So this is the information that I get. Can I get some further information by constructing some other type of observable that act on this system? Okay, that's another story. But what for me the important point is that if you make the use of the Z2 gradient parastatistics, you get this kind of analysis, which is directly reflected in the degeneracy spectrum of this theory. And of course, this can be some general property, which of course, for more complicated models enter. And for more complicated models, you have to analyze a role of Klein operator or R symmetry and so on and so on.
Actually, I have one question. So I got confused a little bit. You started from DFF model. In that case, your operator P and Q are differential operators, right? But when you switch the statistics, when you transmute the statistics, if you keep the original differential operators, you can, what happened to the wave functions? Because you have more degeneracy. So I'm wondering what is the wave function, for instance, in this case?
Thanks for the question, because this is just, you see, the point
On the microphone?
Yeah, but you see, the point is the following. All this theory, if I go to one particle case, it's absolutely the same. The spectrum is the same. Nothing changed. Okay? Absolutely nothing changed. What changed is, and one way to see that it doesn't change, because you want to have a statistics of the particle, which tells how the particles are behaving when you flip one to another, like what happened with bosons and fermions. But you see, everything here is contained in, sorry, go here, in this, in the coproduct. You construct a wave function which depend on 2 positions. So if the single particle contain only is determined by X, now you have a wave function which is determined by X and Y, which are the position of the 2 particles. So the vacuum is the same. You start computing the first excited state in this way. So due to this, you have some contribution from X and contribution from Y. And then when you go to the second energy level already, second excited level, already you have some contribution, which in some cases can disappear due to the fact that these sign that are all these possible choices of that. There are 8 choices of the sign which correspond to the 6th type of statistics and parastatistics. And you see, when you have this kind of choice of sign, then you have that this particle here this creation operator are the same as this one. So the ray vector is the same. So that you don't have a new vector. And that affects the generacy. In the bosonic case, purely bosonic case of fermion boson, there are no such kind of relations. So that's why you have all four excited states. But in the fermionic case, where both are satisfied, you have only two excited states at the second level. But in the parabosonic case, which are obtained from this absolutely idiotic algebra, they're not even minimal algebra in the sense that we did with Gianna, because this parabosonic algebra is something like that. You have 0, 0, 1, 0, 0, 1, 1, 1. This is color algebra, Z2, Z2 color algebra. And here you put P, here you put Q, and here you put empty and empty. It's look idiotic, but he has the consequence that to give this kind of relation, which is not reproduced by any of the ordinary statistics for the same set of operators. Right? Sure, of course. Yeah, and this is why we used the alpha Fubini-Furlan, because you know, you have a well-defined ground state, and then you have a discretized energy level, and you resolve everything in terms of a very simple, nice combinatories that can be analyzed with these idiotic tools, right?
So if not, thank the speaker again. Okay, so this is the end of the meeting. You want to say something?
Sorry. Well, first of all, I'm sorry because this is a very tiring day, long day for all of you. But I hope now we will have some relax together. I want to thank in particular first the person who came from abroad, like Professor Naruhiko Aizawa from long way from Japan. Then Mauricio Valenzuela, because it's a little bit closer from Chile. So here we always did this. Then, of course, Gianna from UFABC, and thank for the student, because it is great to have a participation of student in this kind of workshop. And this, I really wanted to have the possibility for you to express yourself and to ask questions, to be that and to be involved in this active discussion. And then, sorry, last but not least, she was great. And I'm sorry, you were really great. I think you deserve a great applause, Anna. And no, but this is an extra point. So we should also congratulate one of us that instead of spending his honeymoon, he's with us, making presentation and staying all day with us. Mateus, congratulations, Mateus. Okay, and then thank you.
Let's thank the organizer for all the work. Thank you very much, Francesco, for the nice workshop. It's always inspiring to listen a lot of talks and young people. I want to remember when one was a student, and also listening interesting talks and topics. One gets idea and takes notes and thinking like future projects. So thanks, Francesco, for the organization. Okay,
now time to have relaxation.